Okay, so let's get going again. We're on video number 72. I had to do dinner with my mom, so today's her birthday, so I had to interrupt the previous stream. But let's see what we gotta do now. Let's look at the agenda screen here. Yeah, we're doing all of this stuff all at once, except for number 6. We're doing 2 through 5 all at once right now, which is not advisable, but that's the way it has ended up going. So, if we look at what needs to be done, we can see down here, finish this formula, right? And we have some type of formula. And we need to finish it. Okay, all this stuff. Too much stuff, too much stuff. Glock picks to pain picks. So all of this stuff here represents the Glock picks, I believe? No. This represents Glock picks. These are inputs, our outputs are pointers. So this represents pain picks. The tile quadrant, the tile exponent, the tile layer, and the local TX and TY. If you want to find a diagram for that, this is pretty good, right? So our tile quadrant is one of these guys right here. Our tile layer is going to be one of these guys here. The tile exponent corresponds to which size, right? So there's these big tiles, or not big tiles, but many tiles, many small tiles, less smaller tiles, or less bigger tiles, and less even bigger tiles, right? And then down here there's one gigantic huge tile that covers the whole canvas. Okay, references can never be null. That's a good little check. Bounds check on that input. Make sure that the that max glow tx is not greater than or equal to glow tx. Let's think about that for a second. Yeah, that makes sense, right? Man, I can't believe I actually was able to process that backwards. But yeah, we want to make sure that glow tx is less than or equal to the max tx value. That's basically what that is. So a little bounds check. We're going to get those variables ready. Looks like we have int16 versions of a lot of these variables. Let's go highlight the main variables that we're going to be working with right now to try to be able to focus in on what we need to be looking at here. So here we see these i16 versions of the variables. When I say i16, I just mean a signed 16-bit integer. And a little macro to calculate the 2D location. So ASCII picks to diag picks, and some stuff. So paint picks to diag picks, or diag picks converted to tile exponent. So we have this diag picks here, and we're getting the tile exponent back. So I think at some point we need to calculate all the index locations for everything. So everything, the tile quadrant, the tile exponent, the tile layer, all three of those things should have a two-dimensional manifestation. So we see tile quad is the first thing, and tile quad width is 2x2 cells. So we need to do something very similar for everything else. So do we have an XY for everything else, or what is this? What's going on here? Oh, X. Oh, what? 1D. Okay, never mind. This is 1D. We're going in the opposite way because we got all the 2D stuff over here. Okay. So the tile quadrant, the tile exponent does not have any type of 2D representation, does it? Tile exponent kind of tells us what size we're using, but it's just used to get other things. So yeah, tile i16. Okay, so the tile exponent here. Tile quad. So we need to get this tile layer, I guess would be the next thing. We need to figure out which one we're on. How are we doing that? I have no clue right now. Okay. So let's pretend that we know what we're doing for a second. And I noticed that we have this, like, i16, tile layer, most likely. And we probably have, like, an OX lay, maybe. Plus, till lay width. And it's a 2x2 map as well. And then OY lay is kind of what I would expect if we're being consistent here. So let's look up here and see, do we have a thing called OX lay, or do we not? We have OX qua, but we don't have OX lay. So let's just say this is XY location of til qua, right? So til qua, that's what that is. And we need something else for the layers. So I don't know exactly where it belongs. I guess since it was an afterthought, I guess we should post it down here. I don't know if it really matters, but OX lay, and we'll just do, you know, 0 minus, let's just keep on doing this 2002 thing. Okay, so OX lay, and this is going to be the XY location. XY location of this thing, right? Okay. So we're gonna kind of, right, there's all these variables. We don't really know what's missing and what needs to be finished. And so we're just going to attack the problem from any place we can sink our teeth into. So this OX lay, OY lay thing, right, we can use OX lay, OY lay right here, and we can get this two-dimensional tile lay location, right? And that needs to be, that's right over here. Okay, so that's something we actually did need to calculate. And then over here, right, we can define til lay width, which is also 2. And the thing I don't like about using a width variable like this is because when we use a width variable, width and height are both equal to each other. And it kind of bothers me that we have width in these formulas, but we don't really have a height, right? So we might want to make a note that width equals height. We could do this, you know, width equals height like that. And if we did that, 2 by 2 cells where width equals height, we could just write san for span. Which is a little bit more confusing. And we could make a note of that, right? So, at vid IID 0072, and the time is 0 hours, 8 minutes, and let's say 40 seconds. Just say that, you know, san equals span means width equals height. Use this variable to preserve the balance of tokens in our code. And when I mean the balance of tokens, I mean, you know, wherever you have a malloc, you need a free, right? So you have this kind of balance in the code where you should be able to count the mallocs and count the frees and be like, there's exactly the same amount. Well, same thing with the width and the height here. I really do not want to have a different amount of variables that say width and a different amount of variables that say height in my code. I don't care that the formula only uses width, because we're calculating the xy, right? And so it really bothers me that the code is kind of asymmetrical like that. So we're going to use a span variable in our index to xy calculations down here so that we can kind of mitigate the damage of the asymmetrical code. Now, why the hell are we getting these index locations? Like, what is the point of this? Because I really don't know. So let's look at this. To paint pics. Oh, so it's literally because these are the outputs. So that's why. So the a tile quadrant and the tile layer, right? And now this tile exponent, if we look at that, let's kind of highlight that for a second and see where we can find other instances of that. So we have this tile exponent thing here. And the tile exponent, we can calculate that by looking at the diag pix, and that actually gives us the tile exponent. Cool. So, knowing that, the tile exponent is already equal to itself, right? So we can just say tile exponent is already accounted for, but I want to do like I16 tile exponent equals already calculated, my friend. I just want to make it accounted for right here, because I see that we kind of have the quadrant, the exponent, the layer, and then these local tx, ty's, which looks like we're going to whittle down the global amount to get those. So let's look at how we're whittling down this global to get to where we need for this. So here's our global. Okay, our global is still there, I16 GTX, so it looks like we're going to turn this into I16 GTX, and we're going to take, to get the quadrant we're in, we're going to divide by 256 and floor it, and then we're going to whittle it off, right? So we're going to whittle it off, and that's going to give us a value within this kind of local range here, with the remainder here. Okay, so now with that remainder, we have the diagonal pixels, and these diagonal pixels need to be the min of the x and y's. Once we have the diagonal pixels, we figure out what our tile exponent is. Okay. And with the tile exponent, what are we doing with that? We just have the tile exponent. But how do we get this x and y location here? So if we know what the tile exponent is, we can figure out the x and y by just kind of figuring out what we're crossing into, right? So, so let's do this over again. So let's do another thing here. So let's actually make a section here. We've been not making sections, but so find, and we're going to say find tile layer XY chord, right? That's kind of what we want to do. Okay. So we want to find this tile layer XY chord, and how are we going to do that? And then we have this OXY. So we could also say, that tile layer XY chord equals OX lay, comma OY lay. Alright, we could make a note of that. Here, can we get that a little bit terser? Yeah, like that. That's kind of odd, but sure, why not? In order to get this, we need to see where we're colliding, and we need that local remainder thing. So this remainder thing is within the 0 to 256 thing. So we just need to figure out, well, with the current tile exponent, what are the size of our tiles, right? So, so this tile exponent here, we need to get, like, the tile size. Tile size in pixels. So till sis means, let's see if we have tile size. How about sip, till sip, right? For tile span in pixels, let's just use that. We're gonna make a little definition over here. And I'm gonna call it tilsip. We're just gonna make this stuff up as we go. So tilsip, tile, span, and pixels. Pixels. So it's for the data layouts, not the visuals. And if we do like something like this, tilsip, then we're gonna expect to spell it properly. And then, you know, tilsip, this is actually not what we want to put this as the tilsip means. So tilsip means, or tilsip means, or tilsip means, or tilsip means, or I don't know, tilsip means, right? Many different ways we could do, but this is the little definition we want for that. And if we do this, we just want a little check mark here. So, hey, you spelled that correctly. Awesome, good for you, right? And if we type it improperly, like siptil, or sip-til, or siptil, we're going to say, hey, backwards, use tilsip, like that. Okay. So now that we have these kind of things here, in our notes, for our shortcuts, we actually want to document them for the rest of everyone, right? That's only in my personal notes. But it helps me kind of formalize things. So tilsip, can we put it over here? Do we really want to do it here? Sure, why not? Having this nice little index here is kind of nice. So I16, let's keep everything the same, just for consistency here. And tilsip is equal to, why don't we do another chat value? And just say, tile size, in actually, I don't think we should call it tilsip for tile size and pixels. It's really like our partition size and pixels, right? It's not a, we could call it sector sip or partition. Partition actually makes more sense. Let's kind of look that up. Should we call it partition or sector? So let's see. Let's look sector versus partition. So I think partition makes the most sense. Oh, or we could call it partition sector, computer knowledge. Okay, you know what we're going to call it? We're going to call it, instead of this, we're going to call it BPS SIP. Okay? Bitmap partition sector. It's going to be bitmap partition sector. Or BM partition sector, because we're out of room. And size in pixels. Right? So that's nice. So let's go with that. And then over in our notes where we kind of said we're going to use this thing, let's change our mind on that. Let's say you know, let's comment this over here so we can find it if we ever want to use it again. Changed my mind. Use bitmap partition sector size in pixels. Okay. So over here, we're also saying, you know, that we changed our mind. Yeah, we changed our mind on that. So let's do the same thing for BPS. So BPS, bitmap partition sector, size in pixels. Okay. If we type this correctly, then we're just going to be shown a check mark in a box. be like, congratulations, you know what you're talking about. You remembered it correctly. So instead of autocomplete, we have an auto quiz, right? Instead of saying, here, show me what my options are, we say, hey, I think this is the option, am I correct? And that, right, so that's a little bit, instead of groping your way around, we're going to quiz our way around and reinforce that we know what we're talking about when we're writing the code. So BPS SIP and BPS SIP, and if we do this, BPS SIP, we're going to just spell it the correct way, right? If it's close enough, then that's just us being lazy on the keyboard and not wanting to type an underscore. If we type it backwards, so SIP BPS or SIP BPS or SIP BPS, then we're going to not allow that. We're just going to say backwards, use BPS SIP. And the reason why we don't just flip it and we actually warn that it's backwards is because a lot of times we just remember it incorrectly. And so we think it's supposed to be one way, but it's the other way. So we don't want to take that lightly and just conveniently flip it back in the way it needs to be. We need to be a little bit more annoying about it. Right. We need to have a stronger learning signal, right? You want to absolutely shove it in your face that, no, you're wrong, flip it around, right? Negative reinforcement and positive reinforcement, I think they both work equally effectively. Negative reinforcement is only really bad when it introduces, like, very high levels of mental stress or whatnot. Right, like if you go extreme and you like chop off someone's finger, right? Like, maybe that's not the best negative reinforcement, right? But saying you got something wrong or saying you got something right, like one is negative reinforcement, one is positive reinforcement. It's perfectly fine. So we have one more thing. We want to say, well, what does BPS SIP mean? So BPS SIP means, or BPS SIP means, and then also BPS SIP means, in case we want to use it as like a shortcut in a prompt. And BPS SIP is going to be bitmap partition sector. Okay, and then size in pixels. We can also say, or span in pixels, whatever. Doesn't matter, one or the other, size in pixels, right? Because it's only one-dimensional, so when I say size in pixels, ooh, yeah, we should actually say span in pixels, not size in pixels, because, we might get it confused with number of pixels. So span in pixels. Span means width equals height, not number of pixels. Right, so we want to make sure that it's not number of pixels, right? It's a span. Now, because we have that, and I see the possible mistake of doing something like number of pixel, I think we want to say, like, make some type of thing, well, BPS number of pixels, right? And sure, why not? Let's just do it. So BPS NOP for number of pixels. If you type that correctly, you'll be rewarded with saying, hey, you did it correctly. Awesome. Good job for you. If you type it closely like this, it'll fix it for you. Okay. And if we do it backwards, then you're just in trouble. BPS NOP, BPS, and NOP, BPS. NOP, BPS. Okay, so that's a weird thing. Okay. So backwards, use BPS NOP. Okay. And lastly, well, what does that mean? So BPS NOP means, BPS NOP means, BPS NOP means, and BPS NOP means. Okay, so BPS NOP. BPS nop is bitmap partition sector number of pixels. Total number. Okay, so with that, we have a nice little documentation for this new kind of variable name that we made. And let's go back over to the code and say, okay, we have this thing, we wanted to call it BPS SIP, but we're not going to do that. We're going to say, well, no, BPS SIP is right. Yeah, BPS SIP, size in pixels. But then down here, we had this thing. We're going to say BPS bitmap sector partition. And SIP, size in pixels. And we're looking at one of these sectors here, right? That corresponds to the tile layer. And to get that, we're going to take the tile exponent to the size in pixels somehow. So we can do something like AAC 2020 PAINT5D and till exp C2 something or other. So do we have a function like this? Let's kind of check to see if we have that. So we have this like max coordinate, and I don't know if max coordinate is what we want. Max coordinate, I don't think so. That's also useful, but it's not what we want. So yeah, so we want to be able to convert from tile exponent to tile exponent to I guess we should just call it BSP SIP. Bitmap sector partition, right? That's what we're calling it. Bitmap partition. Oh god, so this is what's gonna go here. Binary space. Okay, so I see a possible. It looks like I am going to end up swapping around BPS and BSP a lot, and that's gonna be bad. I don't want to write code that I'm gonna accidentally swap around variables all the time. So so we're gonna call it bitmap partition. We're gonna call it BipSip for bitmap partition. Bitmap partition size in pixels. BipSip, right? A little bit easier, right? So anywhere we see BSP SIP, we keep on changing our mind on this. Yeah, we'll call it BipSip. BipSip. So bitmap partition, and then span in pixels. BipSip. I like that. So the idea is that it needs to be kind of. I do like it when it's kind of like it has a vowel in the middle, so it's kind of easy to pronounce. And when we have a large amount of if we have a whole bunch of consonants strung together, I have the propensity to mix them up and use them in the wrong order. So we're gonna go back to. We're gonna change our mind once again on here, and we're gonna say like over here. We're going to take this whole thing here, we're going to comment this out, and just be like, nope, changed our mind again. Changed mind again. Use BipSip. Okay. And then we're going to just say backwards and changed mind. Use BipSip. Okay. This thing, change mind, use BipSip. Okay. Same thing with here. changed mind, use bipsip. Changed mind, use bipsip. Okay, so everywhere where we had this idea, we're gonna go right at its conception. We've already changed our mind before we even used it. So same thing with this. What are we gonna use for this? We're gonna say changed mind, use bitmap, right? So bitmap partition number of pixels. Okay, and then over here, same thing. So we're gonna say changed mind, use this. And this is backwards and changed mind, use bipnop, right? So instead of BPS nop, it's bipnop. Okay, so for this, we're gonna comment this out. We're gonna keep a record of it up here in our comments if we ever actually want to get it back. And then we're just gonna say, you know, changed mind and use bipnop. Okay. So we're all over the place on this. So let's finally, hopefully, have settled on something. So bipsip. And if we type bipsip properly, bip and sip u plus bonds hexa. Okay, saying, hey, you typed that correctly, awesome. And if we type it close enough, then it'll correct our spelling. And we're good there. Now, if we type it backwards, we're going to have that warning. Sip bip, or sip bip, or sip bip. We're going to say backwards, use bip sip. Okay. So also we want to know, well, what does this mean? So what does bip sip mean? Bip sip means, bip sip means, and bip sip means, and also just a bip sip means, I guess. Yeah, sure, that looks like enough. And bipsip, what does this mean? It means bitmap partition span in pixels. Span in pixels. Right, because our data is essentially a bitmap. We could be more abstract about it, but the idea is we want our code to be the least abstract as possible. I know that our variables are very terse, but we're actually aiming for code that does not have much abstraction. Right? It has very terse kind of abbreviated variables, but besides that, it has a very kind of definite. We have very strict definitions for everything. So let's take this bipsip thing, and let's take it and do a little FARC template here. And here's our source, and we're going to say, instead of sip, we're going to say nop. So we're going to find sip, and we're going to replace it with nop for number of pixels. Run that. And now we have bipnop. And backwards, this is all good. The thing we need to fix, though, is this bipnop. Bitmap partition span in pixels. This needs to be changed to number of pixels. Total pixels. But we can't really name it top because total pixels, top, T-O for total, and then P for pixels, because that would look like the word top, and that might be a little bit confusing. So NOP for number of pixels is a better choice of acronym, I believe. I could be wrong, but I'm the one making this stuff up, so that's what we're going to work with. Okay. So now we have this function here, bipsip, and I got to think, well, where does this belong, you know? And it probably belongs in somewhere where we have like a tile exponent converted to whatever the heck, right? So somewhere in here, we probably have like max coordinate. So we already have some type of max coordinate conversion function thingy somewhere in here, right? And this is helper functions conversion. So tile exponent to diagpix and max coord. So we have a lot of conversion functions already. And this is pretty much the same deal. It's just as the max coordinate. It's just a little bit different because we're using the size. So actually, can we just paste this? Yeah. To bipsip. Okay. And U08 till exp. And we could just kind of like make this function use the other function, right? Because we see these -1s, but that's not what we're going to do, because we actually don't want these. I would like to keep these helper functions to not have like any interdependencies between them. So this logic here is pretty much all we need. So we can kind of copy this and kind of refactor it a bit here. So we see tile exponent to bitmap partition size in pixels, or span in pixels on one axis. And everything is here. It's just that, you know, let's just do a +0 here. Right, so we can keep the same pattern here, but there's no off by 1, and having a +0 says, yes, we thought about the off by 1s, and we decided, you know, nope, we're good, right? So this thing that says max coordinate here, we just need to change that, right, to bipsip. Bipsip, size in pixels. So this is how many pixels on a given axis that partition has to it, right? So the largest partition is a 128 by 128. The second largest is 64 by 64, 32 by 32, 16 by 16, etc. So that looks good to me. Now, because we have this, we should throw a test function in there. And also, is this being called somewhere so we can find our way back to where we're going? Yeah. So it is being called somewhere. So let's look at this function here and say there should be a test for this somewhere. Probably not using it in too many places, so we should be able to find it somewhere. Brush chords transform, PAINT5D unit test code. Okay, so right here, you put the new function kind of at the top here, so we can kind of paste it down here. We'll make it void and just throw this in here. And it's going to be kind of a simple thing like this as well. It's just, right, we're just kind of, there's really nothing to it. Yeah, there's really nothing to it. We take this function, instead of converting to this, we use bipsip. Instead of all these 120, 127, etc., these are all powers of 2 now. So 128, and we have 64, we got 32, we got 16, we got 8, we got 4, we got 2, and we got 1. Yep. And that's it. That's all we need for that. Now, we have to call it from somewhere, because we're not actually calling it. Like, if we look at this function here, we'll see that it's being called up here. So we need to kind of like copy this and paste our new function in there. So let's take this function and extract this part right here, this part, and throw it into here. And then we'll have the proper function name for this, right? So if we look for where this is, it should be there. We may have named the... Okay, so we probably named that unit test function wrong, didn't we? We kind of hacked it together really quick, and we didn't think about what we were doing here. So we want to take this unit test underscore thing, and we want to put it right before the conversion thing. So right before here, it should be right there like that. And now if we look at this, we should have the correct name. Yeah, so this name right here is just being called in one place with a for declaration before it. Awesome. So we need to clean this up a little bit, because we have no section divider over here, right? We have these two functions, but there's no divider line. So we need to throw a divider line in there so we know that there's, you know, more than one thing, and a divider line here so that even if we see the very beginning of the section, we already know there's more things to come, right? Because we see this dash divider, so we know this is not the only function within this section here. That's just a convention I use. So down here, we should do the same exact... Oh god, there's a lot of stuff in here. Down here, same thing though. I want to put a little dash line there. Yeah, so now that we have that, let's look at this function that we're calling here and make sure that, hey, where are you being called? Because I know we're not finished using you. So tile exponent to bipsip, right? So we want to take that tile exponent and use it to figure out what bipsip is. So this and that. And where are we getting tile exponent? We should actually have it somewhere, but it may be a different type or something. We see tile exponent here. Notice that it's it's this pointer thing. And so it looks like we're going to use like I16 tile exponent. Yeah, so I16 tile exponent is actually what we want to be using there, because we don't want to touch any of these variables that are pointers until we're done doing all of the calculations, just because it's going to make our lives a lot easier if we kind of isolate the math logic from the pointer logic. Okay, so I16 tile exponent, this BSP SIP, and this should be BIP SIP now, so BIP SIP. And, okay, cool, so we got BIP SIP. And we're trying to find the tile layer XY coordinates. So we figured out how big the partition is, right? And now we can do some simple tile map collision math with whatever this remainder is. So this remainder here, which we willed off 256, so it's in a 256 by 256 area. And even though it is in a 256 by 256 area, we have to chop off the diagonal, don't we? Yeah, we do have to chop off the diagonal. So we have this thing, we have the quad, and then over here we have this diagonal pixels, and we have to chop off those diagonal pixels. So we got the diag pix. The diagonal pixels will tell us, we're going to use those diag pixels to figure out the tile exponent, and that's great and all. But we need to chop off the remainder of the diagonal pixels to get something local again. So we're going to take the remainder, and once we get the diagonal pixels, like a lot of these calculations we can do in different orders. We should do them right when we need them, I guess. I don't know. So each calculation that needs to chop something off should probably chop it off right away. So rem ix equals rem ix minus diag px. Or actually, diag pix, right? Because these are both equal here. So minus diag pix here. And then the y is the same thing. So the y right here, diag pix. Okay. So we really should have some type of better organization here, right? We have like this kind of stuff all floating around. And I'm not really a fan of, this just seems kind of ugly. So let's kind of divide this up and say we got to calculate something and then rebase, or rebase our local, right? So, so this quad here, get calc til quad Alright, we're calculating tile quad. Calc and rebase local. Right, that's what we're doing. We're calc and rebase local. That's kind of what's going on here. This thing here, all this commentary here, is now local to dia selected tilqua something or other, some commentary. Okay, sure. So we have enough room where we can kind of indent that a little bit more. So let's take advantage of that. And I'm just trying to figure out, like, all the calculations kind of merge into each other. it's like trying to say, like, you know, with, like, decades, right? The 2000s, the 2010s, 70s, 80s, 90s. It's like an arbitrary distinction, right? But everything, those decades, those years, they actually linearly flow into each other. And you're just taking these, you're just trying to arbitrarily slice, right? And I'm trying to do the same thing, right? All these calculations flow into each other. And so as I'm making these subsections, I'm actually trying to artificially slice up the calculation into sections that actually make sense. So we're going to say calc and rebase to mean we're going to calculate tile quad, but then we're going to rebase the local, right? So this remainder ix, right? This is our rebase, right? So, you know, this is at rebase local. That's what this is doing, right? And this is at calc. All right, so when we're talking about calc and rebase local, that's what what we're doing there, right? So if we want to talk about rebase local and what we're doing, let's make a little kind of notation here. And I may not be using the correct terminology. Like I'm thinking of it as like a change of basis, but I'm not really a math person, so I have a vague understanding of what change of basis means, and I may be using this completely improperly. But we got to have some type of words to grab onto ideas. Otherwise, we can't build abstractions, right? Tools are, you can't go to a higher level of learning or thinking until you have a terminology, right? You can't layer on abstraction until you have a concrete terminology for the current level you're on, right? To get to the next level, you have to have a solid foundation of terminology. So we're going to have to just say it's called rebase local and then describe what that means. I mean whittling down some type of value into type. You start with a global variable, and each time you whittle it down, you have a new coordinate that is local to some type of sub-partition in some data. When I mean rebase local, I mean we are taking another chip away at the remainder value, making it smaller and local to a smaller sub-partition. Summary: get a new smaller local value from a previous local or global accumulator value. Something like that. That's kind of ranty. The terminology isn't quite right, but it's the best I can do. So let's actually make a note here, right? Because we have no clue what we're talking about here. Let's do a video integer ID. And because this is something where someone's going to read it, and they're going to be like, I have no clue what this person means. Let's have the kind of video document here. So, rebase local, right? We're starting with some type of global variable, and each time we whittle it down, we have some new coordinate that is local to some type of partition in some data. When I mean rebase local, I mean we're talking about another chip away at the remainder value, making it smaller and local to a smaller subpartition. Summary: get a new smaller local value from a previous local or global accumulator value. So yeah, if we look at, let's not copy this diagram. So if we look at this diagram right here, so let's take this diagram. Okay, in PAINT5D.data, we could start with a global variable called global x, global y, and assign it to a remainder x, remainder y variable. If we chip away at it by figuring out which 256 block it is in, and then subtracting the block index times 256, we will have at rebase localed to a new xy remainder value that is local to the at tilqua instead of local to the entire 512 by 512 bitmap. Okay, so this is kind of more learning, we could say. Even more explanation, right? So even more explanation of what the hell I mean, because I don't think I'm doing a very, and also let's not use slashes of any sort in here. Now, this isn't actually going to be a code file, but I want to keep to some type of code file convention where we're pretending it could be put inside of a code file. And what I've noticed is backslashes or forward slashes, one or the other, cause a huge problem inside of multi-line comments. So we're going to try to avoid slashes when we can. I know we've probably slipped up a few times, but let's just, when we can remember, let's not do that. Okay, so we got this nice little comment about what we mean by rebase local. Cool. So, calc and rebase local, tile quad. Okay, so after that, what are we doing? So, we have some rebasing here. And this is calculating diag picks and then rebasing local, right? So we're going to try to like do calc and rebase local. Calc and rebase local. And this is diag picks. Or is it diag picks or is there other stuff we're getting? Diag picks is kind of this thing where we get diag picks, but diag picks isn't really the thing we want, right? If we look at this, we want the tile quadrant and the tile exponent, right? And diag picks is like this intermediary where we're going to get the tile exponent, right? Because we use diag picks to get the tile exponent size, right? So let's not call it diag picks. Let's name these sections based on those main pieces of data that we want to calculate and return, right? So instead of calling this diag picks, we're going to call it til exp, right, for tile exponent. Now, it's a little strange because we have this irregularity where before we kind of just rebased at the end here, but now we're kind of rebasing in the middle, aren't we? So calc and rebase. So since it's calc and rebase, we might as well kind of put the calculation here and then the rebasing over here, even though it's kind of split here like that. Yeah, sure, why not? It's not perfect, but it'll do, right? So we'll indent here and then say, okay, we got this offset subtile pixel, and it's local XY, and we're out of room here, right? We're like way out of room, and maybe if we just kind of crunch this in here, we can kind of get that, right? And that's kind of ugly, but it's better than crossing that line, so good. Let's take this same thing, and I notice we have this kind of thing here, and I think that's, we'll take a look at that right after we're done kind of making this section. So, calc and rebase tile exponent, right? And tile exponent, is this thing right here. Do we want to make a note that tile exponent is... Do we just want to do like something like this, where we kind of like do something like I-16? I don't know. I think that could be helpful. It gives it also a little bit of room to breathe as well. So I'm not gonna write it off. I think this could be helpful. So let's go with it. Alright, so wherever we see this tile exponent, we can kind of just shove this right here, right? And that'll kind of help us know what we're talking about. Right, because we have tile exponent, which is the output, and the working variable is actually this int16 tile exponent. And it's the same thing with tile quad, right? So in tile quad here, we don't see it lighting up anywhere, right? We click this and we don't see it lighting up anywhere because because the tile quadrant right now is XY value, right? So do we want to do kind of like these? We said we were kind of do all these indexed XYs right here. So I don't know if that's how I want to do it. We could do that. So let's look at tile quad. And I don't know, man. So we could make a note like that where it's kind of weird, but it'll kind of help us know, make the connections here in the comments where we say tile quad and oh, that's composed of these two things, and oh, these two things are here. It's just this thing isn't here because we're just calculating. We're not calculating the XY yet, so this is kind of ugly. But right now we just need to get it done, and if we ever want to make it nicer, I guess we'll make it nicer. But yeah. So after we have that tile exponent, we're going to rebase using the diagpix, right? The diagpix that tells us if we're like here, or if we're here, or if we're here. And once we've done that, we can use the tile size. So we need that tile size, or the bitmap partition size in pixels, right? That's what we're looking at here. And we're using the tile size exponent, which needed the diagpix to calculate. Cool. And so we're just trying to get the tile layer, right? Yeah, we're trying to get the tile layer. So find layer, whatever. Yeah, so this is what we're doing. So let's remove some of that stuff. So let's say calc and rebase. So calc and rebase local. Oh, we'll call it calc and rebase local, right? So calc and rebase local. Let's keep the same kind of pattern going here. And this is going to be the tile layer. And then over here at the... Yep, here we go. Calc and rebase. I don't know if this commentary is necessary. Oh, I guess, yeah, it kind of is, because tile layer, so here's what we're going to do. We're going to make a little commentary. 1D is tilde, right? And 2D is this, right? So let's kind of do some notation here where we can kind of see what we're talking about a little bit better. So we have one-dimensional and two-dimensional representations of what these are, right? So we can kind of say, you know, okay, so at vid IID 2020, not, Jesus, I was about to do the date, 0072, and the time is 00 hours, 59 minutes, And, okay, just 1 hour. God damn it. 1 hour. 1 hour. 0 minutes. And let's just do 15 seconds. Okay. Okay. So this right here, we're just saying for tile layer, we're trying to calculate, this is the one-dimensional representation of the tile layer, right? 0, 1, or 2, right? Because there's only 3 of them, right? There's not 4 of them, right? Because this 4th cell goes into something else. The 2D representation is the X and the Y of the layer, right? And when we're in this section, we actually want to just calculate that X and Y. So we have the size of the partition, and the remainder, we've already chiseled down the remainder using the diag picks. So the remainder should be in the size range of the maximum coordinate. So we could actually take the, I believe, diag picks to the maximum coordinate for a check here. So we could say max core equals, take this function here, and then we can take that diag picks, right? So this U08 diag picks right here, throw that in there. Okay, and so if I'm correct, let's check this out for a second. Well, first of all, we just copied that. Diag picks to max core is what we want to call this one. So the maximum coordinate. And I thought it was diag picks. Oh, you know what? It's not diag picks, it's tile exponent, right? So we have this tile exponent, and we already know what the tile exponent is, right? This is tile exponent here. So let's do tile exponent till exp to the maximum coordinate. Okay, so this thing here, I don't think it's used in this function anywhere. Doesn't look like it. Okay, cool. So let's make sure that that is the actual function name. Okay, yeah, that's the exact function name. And we're going to use this as a bounds check, right? So we don't actually need this anywhere. It's just for bounds checking. So we'll just say, you know, I16 max core 0 minus 2 for bounds checking. Alright, it's for bounds checking. It's something that we could strip off for efficiency later, but for now, we really care about just getting the code correct. Okay, so we know this remainder should be within the correct bounds. So if rem ix, so let's assert that rem ix is greater than or equal to 0. Okay. We also want to assert, guess what? Rem iy, also greater than or equal to 0. Then we want to assert that rem ix is less than or equal to the maximum coordinate, right? So this maximum coordinate is going to be, well, hold on here. This maximum coordinate, is not quite what we want, is it? Yeah, this check actually is going to come after we whittle down. Yeah, because we're not actually here yet. We're not actually here. IY. We're not actually here. Because for here, we have this, the size of the partition. And right now, the size, the XY could kind of go, right, on the outer partition, we could have this whole 256 range here, right? Because At this tile exponent, this offset is actually 0, so it's still 256 to 256 here, isn't it? Okay, so we could assert that rem ix is less than or equal to, and it should be less than or equal to 255, right? 256 would be outside of the range, right? Because we should at least be kind of in here. So let's add that assert. So rem ix and rem iy. That's the assert we need for here. Now, to figure out where we are on here, we have this ox lay thing, right? Ox lay. And have we used it anywhere yet, or is this correct? So we're using it here to get its index location, but right here we're trying to find its xy location. It looks like no, we have not used that yet. We're still in good standing here. Okay, so ox lay is going to equal the rem ix, and then minus, or divided by, divided by bipsip. And then the oy lay should be the y location. So we got the x location, we got the y location divided by bipsip. And we got to assert here, assert that ox lay is less than or equal to 1. So it's going to be 0 or 1. Right, so it's greater than or equal to 0, and it's less than or equal to 1, right? It's either 0 or 1. Same thing with the y, right? If this is not the case, then it means that our remainder is probably too big. It's likely our remainder is too big, or this value is somehow too small. It could be one or the other. If we've gotten the layer, right? We figured out what tile layer we're on. Then the other thing we need to do is make sure that if 0 and 1, if 1 equals ox lay and 1 equals oy lay, let's actually do let's make this a little bit more consistent. So if this is always true, and this is true, and this is true, then we have a problem, because that means we're in this quadrant here, and we only have 3 layers, right? This other tile is used for the nesting, right? So we have this layer of stuff, this layer of stuff, and this layer of stuff, but this diagonal quadrant is off limits. So if this is here, we're just going to say, air diagonal quad is for nesting, we could say. Okay, cool. So we got all this bounds checking. The next thing, what do we got to do next here? We got to whittle something away, don't we? Yeah, we got to whittle away this remainder. So this remainder, we have, we've done this calculation here, but we actually have to whittle that away. And then we are checking the boundaries, huh? But this max coordinate actually is for the next sector, I think. So let's take this for a second. And let's just paste this over here like that. And what's up with this? Why do we have this extra indentation here? This is left over from stuff. Let's not do that. And look, hey, we also have gained ourselves a little bit extra space here, huh? Okay, so let's calculate the new remainder, right? Because we've been using the remainder, but we haven't rebased it, right? So the idea is we're going to rebase the remainder in each calculation that we do, right? So rem ix equals rem ix minus the ox lay times the size of one of these sectors, huh? And how big is this sector? Okay, so this is our partition size, right? We use the partition size here to figure out which one we're in, and now we need to whittle it off. We need to chop it down to rebase to a new local thing, right? So we figure out what sector we're in here by doing the division, And now we need to do multiplication to calculate the new local coordinates. So this OX lay is going to be times the bipsit. Okay, rem IX, rem IY, bipsit. Okay. And we did this little tag here where we're like at rebase or whatever, or something like that. At calc, and then we had at rebase local. So let's kind of do that. Let's kind of keep these kind of tags here. And diagpix, yeah, that's the correct calculation. At rebase local. The calculation, we're calculating tile exponent here. So where is tile exponent? So tile exponent is right here. So technically, our at calc is over here. Let's write it like this. I don't know. At calc. Okay. So I got the calc and we got the rebase local. And we're going to keep that consistent for each one of these sections, right? Rebase, local, and calc. So let's kind of highlight these. Be like, here's the calc, here's the rebase, right? And then some other junk, right? In this section, we have a calc, we got a rebase. In this section over here, we got a calc and a rebase somewhere, but we don't know where it is because we didn't put those annotations. So when we're looking at this, this is the thing, right? This is the thing that constitutes our tile layer that we want to calc. So this is our at calc. That's the this is the important calculation here. And the rebasing here, this is the rebase right here. So at rebase local, right? So we got calculating and rebasing local. Okay, cool. So once we rebase this, we're actually going to expect that the new leftovers are going to be within the range of this max coordinate here. And like I said, all these calculations kind of merge into each other fluidly, but we're kind of making these artificial distinctions between where one set of calculations ends and the others begins. And we've decided, right, it's kind of, we got to get a feel for this, but we're doing good so far. So the max coordinate, we're going to do this like bounds check. And what's left over right now should be local to one of these tiles. So we have like a local XY coordinate. So this remainder is actually our local coordinate. Like, we're done, actually. So calc and rebase local. And we'll say, you know, it's loc something or other, right? So if we look at this, we have loc tx, loc ty. That's the last calculation, loc tx and loc ty. And that is kind of a beefy section name, which kind of makes it kind of ugly, but oh well, right? Not all of our code is pretty. We can't make it all pretty. A lot of times code is a little bit more organic than we'd like it to be, despite our best efforts to force it into a regular structure. Just sometimes we fail to do so. So this max coordinate, and then yeah, all we gotta do is say like loc tx equals rem ix, right? It's literally whatever left over by this time is just our local tx ty value. Cool. Now, finish this formula. Okay, this part of the formula, that's finished. We can chop that away. Let's make a note of where this is, though. Where are you here? Okay, you're over here. This is where you're used. And calculate XY locations. Yeah, this is the XY locations for the most part. And then index locations. Some things need index location. Not everything needs an index location. The tile quadrant, the tile exponent. But let's take everything that needs to be done, right? So, in order. So let's go way back up to the top and say, let's look at you. What do we need here? Let's highlight these things again. And anything that's missing, we're actually going to fill it in. So these are the things we're actually calculating right now. So we got 5 things. And we see Down here, we got 3 things, but then we have the locals as well. So we're gonna say, you know, int16 loc tx equals already calculated my friend. And, you know, if we're gonna do that repetitively like that, we should kind of do, there we go. That's a very convoluted way to get it to uppercase, but that'll have to do. So already calculated my friend, and then same thing for the ty. So the local ty already calculated. So the reason why we did that is we have the 5 things that we need to calculate right here. And we just want to say, okay, not all of them need to be converted from an index to xy. So I'm not sure how I like this, right? How we kind of tried to make these 2 sections, the 1D index location, and then the 2D xy locations. I think these outer categories were kind of a bad categorization, but we're kind of stuck with it now, and I don't really care too much, right? It's clear enough where we have these nice little sections. So let's just keep it like that, right? Okay, so what's next here? The next part is just packing it, right? Return via output parameters. Right, so we want to return what we're doing using output parameters. So we tried to organize this code so that all of the math would be kind of like a wanted all the math to be, how do you say, we wanted to separate the pointer logic from the math logic just to keep things simple, which is kind of wasteful with variables. And so when we're trying to think about places to optimize, this could be one of them. But for now, we want to get things working. We want to keep things simple, and we can kind of try to fix that around later. So tile quad, tile exponent, tile layer, local tx, local ty. Yeah, all these things we need to set. You'll notice that they're restricted, right? Because none of these should overlap, right? Because that would be kind of erroneous. Okay. So let's actually do this. Actually, all we got to do is take these. And notice that those are all in UO8s, right? They're all 8-bit integers here. So we should do some bounds checking on what we're about to return, right? Right, one last thing of asserts. So right here, we can dereference this and then set it equal to its int16 counterpart. But not just equal to its int16 counterpart. We want to make sure we do like a U08 cast of the I16, right? And because of that, because we're doing this cast, we want to make absolutely sure that there's no information loss. If there's information loss, it means we did the calculations wrong. It means something's out of bounds, right? So, you know, assert I16 tilqua is greater than or equal to 0, right? So everything should be positive. 1, 2, 3, 4, 5. And then also, everything should be less than or equal to 255. So we'll do less than or equal to 255, because that's the range of an 8-bit integer. And all of our values should be in that range. Let's take this right here. Actually, we can take this whole thing, right? We can just take this whole thing and paste it over here. Okay. So just make absolutely sure, because we have been pulling our hair out multiple times because we had problems with implicit casting, so we got to be really careful about that. And yeah, so we're just returning these values, and we're done there. So now the next thing we want to do is, this seemed like a pretty complicated function, so I think it's worthy of highlighting these main things that we're calculating, and going through this function one more time and just being like, hey, does this all make sense, right? Let me check my messages here. Yeah. Okay, so let's go through this. It's a private function. So here is the project namespace. Here's the sub-library namespace, or the subsystem namespace, whatever you would like to call it. This is the actual function name, glockpix to paintpix, or paint pixels. The paint pixels is this thing. It's an implied object. There's reasons for why we're going to use an implied object rather than doing an OP saying, man, we always pass around these parameters together, guess we should make it into object. No, we're not going to do that. We want to kind of like see the data. We want to see what we're actually working with, and not try to hide it in some like container thing. So glockpix conceptually means these variables here. Paint pixels, that means these global tx/tys. Or sorry, oh, I got it reversed there. Sorry. This is glockpix, right? Because it's the global x and y on the 512 by 512 bitmap. So it's some pixel location here, and then this thing here, the paintpix, is all these variables. So it's all the different local values that compose this global coordinate. So the tile quadrant is one of these four things. The tile layer is one of these three things. The tile exponent is the size of one of these three things, because it could be this size of these three things, or it could be this size of these three things, etc. The local tx and ty is after you've figured out exactly which one of these blocks you're in. It's the actual xy location in here, right? So we stripped it down from the global coordinate space to the local coordinate space in one of these partitions. Okay. So that makes sense to me. Hopefully I've described it well enough. So we got these asserts. These are asserts for the inputs. Okay, so we're just making sure that the inputs are not void pointers, because references can never be null. So that's good. Let's highlight these, right? These are the kind of things we want to pay. These are the most important things we want to pay attention to. GlowTX and GlowTY we want to pay attention to as well, but these are the main data points we're really interested in. Now we commented this out, so let's just nuke this. Let's not leave that there. Okay, so bounds check inputs. We have the global tx/ty. We just want to make sure that that's not over bounds. Now, if we're going to check the upper bounds, we really should check the lower bounds, because we can see that right here we've decided to use a signed value. So it could be negative, and negative would be disallowed. So let's assert that, let's put it like right here. Let's assert that 0 is less than or equal to glow tx. And same thing for y, ty. So we can read it backwards. Tx is greater than or equal to 0. Ty is greater than or equal to 0, right? Because it should be in that positive range. These values should never go negative. Okay, so now that we have that, what do we have here? We have some trap values for all 5 of these things we're calculating. These are the int16 versions that we're going to use for the calculations. And then we have an int16 GTX GTY, where we're just going to cast the global tx/ty that was inputted to int16. Now you'll notice that the input is already int16. However, at one point in time, we were using an unsigned 16-bit integer. So rather than kind of get rid of this cast because it's no longer needed, we're going to keep it because it makes it a little bit more robust to change if we decide to change this signature back to unsigned type, right? It protects us a little bit from problems with that signedness. And then we have like all these variables, the remainder, the x and y quadrants, the diagonal pix x and y, and the actual diag pix, that's the min of both the x and y, the layer x and y, the bitmap partition, span in pixels, and this max coordinate. So all those look good. All these variables that we'll be working with. Nice to have them consolidated here. I do kind of like the C-ish style of having the C89 style of kind of saying, here's all the variables you'll be working with, and we put them all in one spot. That is kind of nice. It's a lot of front-loading, but it is nice to have a high-level overview of, here's all the variables we will be juggling today, and here's what they mean, you know? So here are calculating XY locations, right? This label, we didn't think it was that good, but it's good enough. Okay, so we have this GTX, right? GTX, GTY. And that's what we, let's make sure that anything that's X and Y is the correct color, right? Because make sure we don't do any transposition here. So we're going to keep on going through this code, and if we see anything that's X or Y, we're just going to color code it, right? Make sure that these lines match. So dividing by 256, right? So we're going to figure out which one of these big blocks we're in by dividing by 256, because the block size here is 256. We're taking something in the range of 0 to 511, divide by 256 to figure out what cell we're in. Okay. Integer division automatically truncates or floors, so we don't have to worry about that. Okay, so we do all this stuff. We got some commentary over here, that's fine. Assert that it's greater than or equal to 0. You know, if we really want to, if you really want to really get, you know, strict with these asserts, then the other thing we're asserting here, we might as well assert that the IX is less than or equal to 255. It should be in the range of 0 to 255 now, right? And if it's not, then we have a problem. So let's add that assert on in there. Let's move this to the zeros place. And then let's highlight these so we can see that they are the correct values. So we're just kind of highlighting X and Y's to make sure we don't make any transposition errors, because I don't make them much anymore, but the reason I don't make them much anymore is because I'm very paranoid about it like this. Okay, so this looks good, where we get the quadrant location, and once we have this quadrant location for which tile quad area we're in, we're going to use that to rebase right here, rebase our local amount to go on to the next calculation. Okay, so with the next calculation, we have this value that's in the range, you know, 0 to 256, and we're going to use it to calculate these diagonal pixels. Okay, X and Y. Now, for X and Y, the calculations will come out different for the X and Y, and the determining factor of which one of these to pick is whichever one is smallest. So we have this min between the X and Y. This min function is a macro, and it should be a macro local to, oh boy, is it local to this whole thing? Yeah. Okay, it's local, it's over here, and it's already designed to take the types that we're using. Well, hopefully. So why don't we look at that for a second? Let's look at this min function, and we know that diagpix, this is int16 and int16, and this should also be int16, right? It's all int16 right now, right? Is that how we really did it? Well, we see that we kind of said min I16, so we kind of already, by naming it with int16, with its overload at the end, we can kind of tell that, yeah, it's already correct. But let's just look at the signature really quick. Yeah, so the signature is correct. We have a trap value. We have less than or equal to make absolutely sure that we don't end up with this trap value. We could also do something like this. We could also do an assert that this trap value, assert that this is not equal to I16 min, right? Like, I'm pretty sure we didn't screw this up, but if we want some extra assurance, make sure it's not equal to the trap value right here. All right, so there's a reason why at check trap. Okay. Okay. So now that we have this at check trap, let's go over here and make a note of that. What we mean by that. At check trap. Compare assert a value is not equal to a trap value, to a at trap value. I mean, that's really all we mean, right? We don't really mean anything more than that. If you want to know what a trap value is, you got to go to the trap value section of this code base. So let's close this off like that and keep on going here. So we add a little bit more resiliency to this. And it might seem kind of stupid, but I've screwed up these functions. Like if I made this just a less than, if I made these less thans, we'd end up with the trap value, but since I didn't, we're okay. But just because I've made stupid enough mistakes, I just want to make sure that I don't make them again here. So let's go back to here where we've been highlighting the heck out of everything and say, you know what, this min function, I think we're good here. Let's highlight the x and y, make sure they match. Okay, cool. And we're rebasing here, so we see minus diagpix. Diagpix is here. And we have this tile exponent here. Diagpix to tile exponent. So it's nice because we can look at this formula. And because of the way we phrased it, we can see, yep, this is the correct input because we have diagpix, C2 for convert to, and then tile exponent. So that's cool. Tile exponent, awesome. What else needs to be done here? Is this the correct rebase? So if we take one of these corners here, if this is 0, it means we're in one of these big blocks here. If this is 256, it means we're in one of these smaller blocks. If it's 256 plus, did I say 256? I meant 128. 128 here. If it's 128 plus 64, we're in one of these smaller blocks here, etc., etc. And that's what this diagpix value is. It's that diagonal center point, right? So diagpix is one value, but it's equal on both the x and y because this is the diagonal, right? So this rebase, I think that looks correct to me. And we have the tile exponent already telling us what size we're in. And we're going to use that eventually, but why are we not using it? Whatever. So let's go over here and say, okay, we got to eventually use this tile exponent for something. It's probably used down here somewhere. Let's take this. Let's highlight this like a purple. And say, where are you used? Okay, so right here. So we're using this tile exponent size to get the size of the partition in pixels. That's cool. We're going to assert that the XY location right now should be less than or equal to 255. We don't know exactly how big it should be. We don't know exactly how big it is, but we can at least assert that it needs to be less than or equal to 255, because it's like we're somewhere around here. We don't know exactly where, but we're local somewhere to here. We're no longer local to this whole 512 by 512. We're local to like one of these things, or one of these things, or local to one of these things, one of these 4 things, right? Okay. So that looks good. Okay, and then we have this division here to get the x and the y's here. So that looks good. And this is the layer, so it says OX lay. So it means instead of just this layer index, these are indices, but OX lay and OY lay are the XY representations of them. Okay, so bounds checking, it should either be 0 or 1, because it's just a 2x2 grid. And they shouldn't both be 1, right? If they're both 1, that's a problem. Because this cell over here is for more stuff. It's not for these layers. There's only 3 layers, and this cell over here is for more nesting and going deeper and deeper into the other sizes, right? Okay, so that looks good. Rebase, remix, bipsip, whatever. So we take remix minus the tile coordinate we're at times how big that tile is in pixels, and then boom, there we are. That looks good. Okay, cool. So now, maximum coordinate, we're going to take the tile exponent, convert it to the maximum coordinate. So it's the maximum coordinate within, it's the maximum local coordinate within a tile using that tile exponent. We're going to use this maximum coordinate just for bounds checking. It's not actually needed for any calculations, right? So we're going to do some final bounds checking on the remainder, and then if it passes that bounds check, Well, the remainder is what's left over after whittling the global value away through successive reassignments. So now this is our local tx, local ty. We're good. Okay. And these are some tile map sizes for xy's to indices. So y times the width plus the remainder, y times the width plus the remainder, y's and x's. This is qua, lay, qua, lay, qua, lay, qua, lay, qua, lay. Okay, so all that looks lined up. And these are both 2s. Okay, that's good. So everything looks pretty good so far. We got our asserts, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. The lower bound and upper bound asserts. And then finally, 1, 2, 3, 4, and 5 for the outputs. So that all looks great to me. What you might want to do here, though, is just a little bit more alignment here. So we could say, we could put this over here. Right? We have enough room to do it, so why not, you know? We have enough room where we can put these right here on this side. We can line this up. We can get kind of ridiculous about it. And then we can write a little checksum here, right? We can say how many things are supposed to be here. Because we have enough room to do it, so we're going to do it. There should be 5 things. So we're going to go bam, 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 and bam. Right, like that. Okay. So now that we have this, we're going to... Okay, cool. What's next? I mean, that looks good. I mean, we did what we needed to do here. We checked everything. We checked it twice. Right? Dereferences for the outputs. All these checksums are 5. There's not really much else we could do. Right? We went over it twice just to be careful. And, you know, maybe there's still mistakes, but I think we did a pretty good job here. So we're going to save this, and we're going to try to compile, and we're going to see what the next problem is, right? Because we made a lot of mistakes everywhere. I'm scared. I just want my code to run. So air something something. Okay, so we don't have a air macro for this section. No, we don't. So we're going to do define, really simple fix, right? Air, AAC, 2020... PAINT5D is the system, and air for, not air, halt. So the reason I use halt is Alan Turing and the halting problem. Or maybe it's just old school. That's the idea that I want to halt the program. I want to kill the program, right? It's not just an error, it's a fatal error, right? And maybe there could be better words for this, but this is just the convention I've kind of evolved into after writing multiple code bases, right? This is a style that I've kind of fallen into. Okay, so now we have a macro for halting the program. What else we got here? Makes assignment from a pointer from integer without a cast. So we're doing something horrible here. And that's kind of scary. So 644. So this oxlay makes pointer from integer without a cast. Really? What's a pointer here? So one of these things. Okay, so here's what we're gonna do. We're gonna clear all of our tokens here, and we're just gonna be like, are you a pointer, right? Oh, okay. Are you a pointer? Or what about you? Are you a pointer? Are you a pointer? Are you a pointer? What about you? What about you? Right? We want to check all these guys. Be like, are you a pointer? So the quadrant and the layer, we may have just improperly declared these. I'm hoping it's just an improper declaration and we just were kind of stupid somewhere. So we see this here, we see this here. They're not pointers. They're int 16s. Int 16s. So everywhere I see int 16s. Now if we look at int 16, we see int 16. Okay, that looks good. So assignment makes pointer from integer without a cast. On 644. You're kidding me. You're kidding me, right? Because I don't see anything about a pointer. 644. Oh, what the hell? I'm looking at all the wrong stuff, because this is not highlighted at all. None of this is. So the problem here... Well, let's take this for a second. So it's this thing here. These guys. I'm gonna guess the local TX, local TY is a pointer, because it doesn't have an I-16 in front of it. And if we look over here, this is I-16, whatever the heck, right? So we should assign this to the I-16, not the, right? Because loc whatever the heck is a pointer, right? So, right, remember how we're going to separate our pointer math from our we wanted to separate our pointer logic from our math, right? Which may be a little bit inefficient, but it makes things a little bit less error prone. So, so we don't want, so this right here, these are pointers. They're the output parameters, that's why they're pointers. So we actually want to do I-16 local, whatever the heck like that, right? We can even see that it's correctly written right here. Well, we just didn't write it correctly here. Okay, cool. So we fixed that. Like I said, even though we double-checked it, I was kind of like, yeah, we double-checked it, but it doesn't mean we didn't make any mistakes. Unfortunately, it would be nice if you could just double-check something and then boom, no mistakes. I mean, if it was that easy, you wouldn't have to write test code. Well, that's kind of oversimplification, because test code also helps prevent accidental changes to your code. But, yeah, it's never that simple. I wish I was that smart, but I'm not, so... Okay. Let's give that a run and see if that kind of works, or see if we can at least get out of this function we're writing, right? So we have this restrict, and we may have just used the restrict in the wrong order again, because I know we did it in the wrong order in some other places. So 704, it looks like it isn't a new function. Yeah, we have this restrict over here. It's the complementary function to this function, and we had to move around the restrict here, because we had to look it up and be like, oh yeah, we don't know how to use restrict, it seems. So for these pointers, they need to be at different memory addresses, so we're putting kind of restrict right in here. But we don't want to lose any space, because there's not much space, right? There's not much space to write all these signatures, and so we're like, just, you know, make a macro for restrict, and then it looks like we also allowed ourselves some extra space there, like that. There we go. I don't know if that's how we did it here. Do we have some extra space in the middle? No. I think originally we probably did. I think it looks better that way. Like if we do this like that. I don't know if it really matters too much, but I kind of like that better. I don't know. Whatever. It doesn't matter too much. It's just that I have this thing where, well, if this is lined up here, then when I go all the way down here, I want to assume that I am consistent enough that, right, boom, still lines up, right? I want everything to be that level of consistency. Yeah, so we moved around the restrict keyword to where it needs to be. What's next? What do we got to do here? Some stuff, blah, stuff, all over the place. Well, the first thing is we got to check the logic, right? We already did one function. We need to check the complementary. So let's get rid of the easy stuff, right? References can never be null. Just checking to make sure that it's not a null pointer. Okay, cool. Doesn't matter what the value is, because we're going to overwrite it. Bounds check inputs. So we have these max values for the quadrant, the exponent, and the layer. And we could actually take a look at those and see, well, what are those maxes, right? So we could go into, it says PAINT5D max, whatever the heck. So we know it's in the PAINT5D data thing. And we can see, hey, look, we got some enumerations for that. So we have, 372. So another thing we could do to make the code a little bit more readable is say, assert that, and we could take these and say, this is equal to 3, right? So rather than having to look it up again, if we have asserts and the code is running, then we know it's correct. So we can go 3, 7, and 2. And then we can take these guys, just be like, qua exponle, yes. So qua exponle, sounds like I'm speaking Pig Latin. So qua exponle, and the quadrant is Is that supposed to be 3? That doesn't actually seem right. So let's look at the diagram, and these are the actual values, but let's make sure that they're actually correct. So looking at the diagrams here, Tilqua is 0, 1, 2, or 3. Okay, so that is correct, the 3. Okay, how about tile exponent? Tile exponent can be 0 to 7, I know, for this. And we'd actually have to look at this data over... Doesn't look like we really have it, but we can kind of derive... this is the last usable slot, because this is just 1 pixel, and we need clusters of 3 groups, so 1 pixel cannot make 3 groups, because remember there's 3 layers for each kind of set of tiles of different sizes. So this 8, and this is 1 based, so we got to subtract 1 to get the index of this 8, and the index of that 8 is a 7, and we have a 7 here. Okay, cool. That's a little bit convoluted, but whatever, we checked it. The tile layer, 0, 1, or 2. So you'd be like, well, why 0, 1, or 2? Why only 3 coordinates? If we look at the tile layer, 0, 1, or 2, right? So this 0, this 1, or this 2, because the third slot right here, the third index here, is used for more nesting for tiles of different sizes. So that's why that's that way. So now when we read this code, for the bounds check, we can not have to look at the other file if we don't want to. We can just look at these and be, oh, 3, 7, and 2, and these 3, 7, and 2, these numbers are gonna jog our memory as to what the heck these things mean, right? Okay, so we're bounds checking. We got this max coordinate. It's a U08 value, and we have tile exponent to max coordinate. So we automatically know that, I kind of see how we did this, where we're like, tile exponent is converted to max coordinate. I remember that's how I wrote it, and I'm like, yeah, that makes sense. But I'm going to say that I don't really like that. I actually think it makes more sense if we line it up like this, and if we really want to, you know, be crazy about it, then what we really want to do is something more like this, where we want to, like, take this U08 and just be like, you know, max coordinate equals this, right? So, or not here. I want to put this here like that. Right, so we want to line up what we're using here. Now, the problem with that is that it's just ugly as heck, right? And then we might want to put another parenthesis here. So that one's there, that one's there. And that's actually kind of really weird. Why do we do that? That's kind of stupid. Yeah, like this is confusing the heck out of me, I must say. This is braced here, and then we have a statement inside here for no reason, really. And then this is here. Okay, you know what? Whatever, it's balanced, right? As long as it runs. The important thing I really want to see is, here's this function, and we can see what goes into it, and we can see that it converts to this, right? So we just want to write it in a way where we can see the flow of what's going on there. Even though it is kind of, like, ugly there. Why don't we kind of shove in max coordinate like that? So that way we can, because I know it's way over here, it's way over on this edge, so we can see it over here like this. That's kind of odd. But I kind of like it like that. And also we can kind of line that up like that. Yeah, that looks good. Okay, cool. Okay, so it's, yeah, this is weird as hell, right? But I can see that we have the correct parameters. This is the important thing, right? I want to see this lined up. So maximum coordinate, and we're going to assert the maximum coordinate is greater than or equal to local tx. So hold our horses here. That's a little bit weird to write. Local tx is less than or equal to the max coordinate? Yes, so okay. Makes sense. We just wrote it kind of backwards to make sure that we didn't accidentally... And local tx is an unsigned value, so we don't have to bounds check it, but if we want to bounds check it, we can say that, you know, we can assert that 0 is less than or equal to this, and then to make this actually work, right, we're going to have to do, like, int 16 cast. Oh, what kind of things do we have? We got an int 16 here, yeah. So let's do an int 16 cast, and we have to kind of do like really weird stuff right now to get this to work, because we're gonna have to do like an int 16 cast plus 0. And just weird, we're gonna have to wrap it like this just so the compiler doesn't complain and say, hey, the range of this never can be less than 0 because it's an unsigned value. Well, what if we change the signature, right? I just want to make sure that we have some protection against if the signature changes in the future. I want to be able to check that lower bound. So we're gonna wrap it like this, like crazy. Check all our parentheses. So we got 3 on this side, we got 3 on that side, we're good. Well, actually, are we good? Because this is 1, 2, 3. Oh, this is a 4th. 1, 1, 2, 3. That's a 4th. Okay, yeah. So that's fine. That works. I feel like I might want to give this a little bit more room, because I got kind of confused there when I was looking at it. Actually, I like the max chord here because it lines up with here, though. Sure. Okay, whatever. So right now, what have we really done? We've checked the inputs and whatnot, but we haven't actually done any calculations yet. So we have this like temp x and temp y, the x location and y location of the quadrant, the diagonal pixels, the x and y of the layer, the int 16 GTX GTY, which is just an int 16 of global TX, global TY. Nice little comment there for me. We could also say, we could have a commentary here for this quadrant here, that this is til qua dot x. Like if til qua was an object, right, then that's kind of like what it would be, right? And til qua dot y, that's kind of what that would be. And same thing with the layers here, right? So we could say that this layer, that's going to be til lay.x and y as well. Right, so just an idea of like how we want to think about that, right? So this is the xy, and this is an index variable, but we're saying of this index variable, if we want to derive the x and y, we would do that. So it's just a little shorthand for me to think about it like that. These are just temporary, so this is a temporary integer x. Let's not do uppercase x like that. Let's just keep it lowercase. And this one here is temporary integer y. Since we're really close to that border, let's kind of move that like that. Sure. Okay. So we know what all the variables we're working with are, or do we? We got some more stuff here. So right now, I think this could use some more organization. So yeah, because we have all these sections, then all of a sudden it's like no more sections. And I see we have a kind of a very clear section of just declaring our variables, which is nice, right? So what is this? I16 is not enough addressing space, blah, blah, blah. I don't think that applies. I'm not sure what that applies to. Like, does it apply to above or below? Usually we put the commentary above what we're talking about. So, but we see this I16 here, which makes me think that it's actually for this section, right? Because, yeah, I'm going to say that it actually applies to all this, that this commentary is not above, it's actually below what it's referring to. That's why I don't like, that's why I like sections like this, where you see, here's the beginning of this comment, here's the end of that comment, and everything in between applies to it. Because then when I look at a comment like this that doesn't have that indicator of the region it applies to, like, I'm like, does this apply to below or above? And I hate having that problem. So let's rename this to temp integer, because we're out of some room again. And let's just say, you know, declare all variables is what this section is. And oh, what time is it? So we've only been going for about 2 hours. So right here, we're going to say declare all variables as well. Okay, cool. So my goal here, I think, is just to get this stuff running, and then I'm just sick of this, but I just want to not have this code in a completely broken state. I want to at least get it compiling and maybe crashing on a unit test or some type of assertion or something, you know. What else? Declare all variables. Okay, so there's our calculations. What are we calculating again? So this is our calculation. So why don't we take this and say calculate. Right, this is actually where we're doing all the code, right? So we got a whole bunch of crap, and then finally we actually get to, here's where we're calculating stuff. Okay. Cool, cool, cool. Okay. So let's take a look at this. This temp value equals the tile quadrant. Okay, so this is like index to xy formula. So the tile quad is this thing, right? So we're taking this tile quadrant and one of these big quadrants, and we're figuring out which one we're in. Temp ix, temp iy. And temp, really, we should just call it Remy, right? Because that's what we were using for the other formula. And I think that was kind of cool because we were kind of whittling it down, but let's just make sure the logic kind of makes sense here. So divide by 2, or modulus by 2 to get the remainder, and the remainder is always our x. Okay, take that remainder off of our 1D collection of values, and then once we take off the remainder, it's going to be evenly divisible by 2. That's going to give us the number of full rows, which is our y. Okay, that looks good to me. And this is an x and a y, right? This is an x and a y. Now, why is this not immediately assigned to... why is this not immediately assigned to something? Because this would be this OX qua. This is a remainder here. Or this is not a remainder, but right, this temp times 256. That gives us this gives us the offset. Offset x. Oh. It's the offset. And we don't call it offset over here, do we? What do we call it? Oh, I see. It's not called offset here. So this is really a, OX qua here is really like cell. Is really a cell X, cell Y. So we might want to change, that to like, OX, OY, change to CX, CY for cell instead of offset. So this is just a bad variable naming, right? We're looking at these names and we're confused because we're looking at those names and we reuse them in that function, but they're not being used properly from what we're seeing here. So calculate this thing here. So yeah, the offset x, offset y, that actually makes sense because we're going to take this temporary value that we used to calculate the xy of what cell, and we're going to multiply by 256. So that actually is correct for this offset. It looks like we're just calculating a whole bunch of offsets and we're stringing them together. The diagonal pixels, we're going to take the tile exponent to diagpix. Okay, pretty simple. Now we did say that it made a little bit more sense to put tile exponent right here so we know that we're properly using it. Diagpix is an offset both for the x and y, right, because they're equal on the x and y. So we don't have to do anything more there. That's why it's right there. Okay, so this temp x, temp y, we're taking the tile layer, right? So there's no whittling away here, right? We can take each component and calculate its x and y offset, and then we can string them together and add them all at once, right? Okay, so x is the remainder. That's why I have modulus here. We're going to take away the remainder from our 1D collection so that it's evenly divisible by 2 here. And that gives us the number of full rows. That looks good. Now that we have an x and y location, we're going to multiply the x and y by the maximum coordinate plus 1, because we want to account for being off by 1, but hey, where is max coord? Oh, it's right there. It's right up there. Okay. Now, we could use a different function. We made another function for this, but we already did max core plus 1, so we're just going to... got some deja vu here. Somebody going to come down here and bother me soon? I don't know. I got this really paranoid deja vu. Yeah. Hold on. Just make a note somewhere. Let's do... Hey, I got a notes file. It's just right over here. @vid IID 0272 time. And the time is 2 hours, 0 minutes, and 33 seconds. Got some paranoid deja vu and think someone is about to come downstairs to bother me. Okay, anyways. I don't know if that's true, but whenever I have deja vu, I like to document it and see if I'm correct. Especially when it's like a deja vu of like something I think that's about to happen, because it's interesting when it does. I believe the universe is deterministic, and just what happens is we forget the day-to-day grind of our lives. We forget most of it. And so we don't really realize how habitual we are. And we're so habitual that our subconscious mind picks up on slight patterns of how things have happened in the past, and that deja vu is just detecting those patterns that we're unaware of. And so we think, oh god, deja vu, or oh my god, I totally predicted the future, but it's really just a subconscious kind of thing. But still, makes me paranoid. Temp X, so we take this tile layer. Tile layer is, where are you calculated? Are you just like input? Yeah, tile layer is input. So indexed XY formula gets that XY location of this one-dimensional layer location thing. And then we're going to get the offset by taking the temp cell location times the maximum coordinate for whatever cell size we're in. So the max cell size, so we take the maximum coordinate of the cell size for the current tile exponent. So that looks good. Another thing we want to do, since we're here, is we want to say that, you know, if 1 and OX lay and 1 oh, not OX lay, but it's gonna be this right now. We're gonna do an error. Both cell chords cannot be 1. Right? Because once again, both cell coordinates can't be 1, because if we look at PAINT5D data, that would mean we're in here, right? And we only have 3 layers, 3 of these layers here. So 0, 1, 2, and 2, right? We also want to assert, since we're here, might as well assert that tempi x is greater than 0, greater than equal to 0, and tempi y, x is less than or equal to 0 and 1. So it's between 0 and 1, right? So we can just make that a little assert here. Any little things that we can kind of throw in there to make the calculations a little bit more robust, like I'm down for. So, we'll just air check the range of temp. We'll kind of make that a little section so where we can kind of easily slide over it with our eyes if we don't want to look at it, because it doesn't pertain to the whole formula. It's just a little distraction, right? All the air checking kind of adds all this distraction, which kind of sucks. As somebody on LinkedIn once said, it's like having a a notebook inside of a gearbox almost. Alright, so after we have all that stuff, let's take all of this stuff and be like, hey, you, and you, and you, and you for the X. Do we have all that? We got the cyan, we got this orange, we got this yellow, and this purple. Where are you? You are just an input, right? Yeah, you're an input. You're good. And we even have a error checking on the bounds of that local TX, TY already. Cool. And let's do the other one. Let's do the Ys. Let's kind of spot check that. So we're just going to accumulate all these things to get the global value. Okay, so does that make sense? We got this here, we got that. We just make sure we got all the colors, right? And the purple. The purple up here. Cool. And we're just going to add them all together, right? Add them all together, and then we got our thing, right? And then we're just going to assert that it's between 0 and 512 minus 1, and then we're going to dereference and assign, and then we're good. Awesome. So dereference and assign. Okay, so now another quick thing we might want to do is, oh, that was horrible. X's and Y's, X's and Y's. So another thing we might want to do is just look at where anywhere it's X's, just be like, hey, X is your one color, Y is your one color, and just a quick spot check to be like, hey, is there anywhere where we screwed this up? Let's look around here and just spot check to see if anything. So already I found a spot. Look at this spot check here. I mean, it wouldn't be horrible. It wouldn't be horrible. It wouldn't hurt us. But it would still be kind of, it's still not good, right? It's still a mistake, even though it wouldn't lead to a bug in the code. It wouldn't lead to the code functioning improperly, but I would still consider it a bug. So let's do this again. X and Y, right? Just a spot check. Make sure that everything looks good. So we still have this kind of asymmetry thing here, and I wonder why that is. So it's because we did the X and the Y. I fixed it, but I did it in the wrong order. So let's put this over here, and let's do that one more time, right? Anytime I make a change, all right, I'm going to spot check, and if I find a mistake, we're going to spot check all over again. And the reason for that is we want to, well, we want to be thorough, and we want I guess for safety, it makes sense that if we check around for mistakes and we see a mistake, oh, that got our attention, let's fix it. Okay, now we need to do another sweep, see if there's any mistakes, and only after we have a sweep where we haven't found any mistakes is when we stop. Is that superstitious? Is this like some type of empirical way that actually works, or is this just me having this kind of habitual thing that I do? I don't know, but it seems like a good idea, but I don't have any like science to back like the statistics of if that actually statistically improves my chances of getting out of here without having any horrible mistakes. So let's look at the X's and Y's here. So we have this X's and Y's, X's and Y's. Just look, do we have any places where things are not lined up? So it looks like we're good here as far as the colors are lining up. Now, as far as like these things, let's just color that purple. Let's color that purple. Color that purple. Tile exponent. Tile exponent, tile exponent. Okay, yeah, so that looks pretty good to me. I mean, I don't know. There could still be mistakes. Like, we checked around, but it still doesn't mean there's not mistakes. But the compiler can only help us with so many things, like this, for example. So U08, and is that in this kind of section here? It looks like it is, so... Really? Okay, well... no. It must be in a different section. So if we go down to 814, it must be a new section. Yeah, 814, okay. So we're in a new section. And quirk map, put get. We got the puts before the gets, and that was intentional. And we see those big messages of AS, whatever the heck. AS, right? We haven't done these yet. And so finally, we're back to kind of where we started a few days ago. Before we kind of spread off and like, oh god, we need all these helper functions. We need all these test cases. We're kind of back to where we started. So that's cool. but now we got to do this. So the first thing is, let's kind of remove this extra line here. And yeah, then we got to start writing this. So let's kind of save our progress so far. So let's just go git bash here and git status, git add dot, git commit dash am, to do paint5d git paint5d put, right? The main git put functions need to be done now. Okay. Okay. What next? I don't know what's next. I'm kind of tired. It's 2 hours, which means we need to do 10 sets of... We need not 10 sets, but 10 push-ups, 10 crunches, and 10 squats. But we need to do that twice because one grouping of all of that per hour. So if we look at our break, we've done 40. So that means that we've been streaming for collectively today for, well, it's 12:41, so we've kind of leaked in the other day. But let's just call this the same day. I guess, did we start before midnight? Well, I hope we did. 12:41. Yeah, we would have started before yesterday, so that's okay. So what day is it? It was Friday. Now it's Saturday. Saturday. We're allowed to work Saturday. Yes, we're allowed to work Saturday. Okay, so we're gonna do some of that exercise that we need to do. So we're gonna do our push-ups right now, and if we can, we'll try to get 30 in, just so we don't have to do some later. We'll see how we feel when we get on the floor. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay. Squats. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, I don't feel like doing more, so... Okay, so that's 20 more. So let's edit this. So that's 20 more. So now we're at 60. And we did like 4 hours. And this is 2 plus. But we don't know when the stream is ending. Okay, so let's go back to the bottom of the screen here and think about what needs to be done now. The put and get functions are just going to use our coordinate conversion functions to do what they need to do. So it shouldn't be too hard to write these functions. We just have to do it. Before that, I need to take a break. So I just gotta get some tea or some hot chocolate or something. And so I'll be right back. Let's go to a break. Let's say 10-minute break should be fine, I think. Let's do break. And yeah. if we feel like it when we get back from break, if we have a little bit of time, maybe we'll do a little bit more push-ups. Try to get to like 100 in a day, right? But we'll see. Okay. I need my cup.
I actually don't know where to start. I'm so furious. And I'm so sad for our country.
All right. Let's at least get these kind of like, let's get these easy things done, and let's call it a day. Right, let's get these easy things done, do our 10 more push-ups or whatnot. I guess we should try to get to 100. But this put function, let's figure that out. If we look at our notes, we actually have like notes for the conversion, so the Glock pix to pane pix. This is what we need in order to calculate the location of the pixel we're looking at. So let's so there's going to be some commonality between the get and the put, because both the get and the put are going to require that we know what pixel we're getting or putting. So this is, right here, we can see that this is a pane pix, right? Because when we're putting, we're using the paint pixel location. And then when we're getting, it should also be the pane pix location, right? It should be the pane pix, yeah. For the get and the put, it's the same index calculation. So we want to take, this is the pane pix, so we want to turn pane pix into a global pixel. So let's take this function right here, just throw it in there, bam, throw it in there, and we're returning via a pointer here. So let's do a declare variables section. I don't know how much time I spend on these sections. I feel like I really need to make some type of macro for this, but for now, too bad we're stuck like this. So, int 16, glow tx, and global ty, right? So this global tx, global ty location right here. And all these guys are already right here, right? They're already there for us. It's just this thing here, we're kind of trying to get that, right? So let's take away this. And the restrict thing obviously can't be there. And this needs to be indented one more time, because what we're going to do here is, this is a... what are we doing here, I guess is what I mean to say. And we are getting the pixel location of all of this stuff, right? The pixel location and the offset and the tile value stuff, that comes later into how we're going to pack bits into the pixel, right? So, get pixel, get XY location of pixel storing data. That is a bit verbose for me, but it describes exactly what's going on, so get XY location of pixel storing data. That is what it does. So that's good enough, right? Okay, after we have the XY location of that pixel, we have to convert the XY location into an index, right? Because the index is going to allow us to actually get the pixel. Okay, so for that, convert pixel XY to index. And this is the pixel location. Remember, this is still in pixels. Eventually, we got to think about in terms of components. But right now, we're thinking in terms of pixels. Okay, let me get some tea here. So to do the index to XY for pixels, well, how about this? XY to index C99, or C11, doesn't really matter. And we have a nice little formula here. The width now is going to be 512. So we could say define mapsan as 512. Width equals height. Right? Width equals height equals san, right? So that's what I mean. By san, I mean span. And I'm just doing san to eliminate the need to... I want to eliminate a lot of the asymmetricalness in the code. So using a span variable for this instead of a width variable, so there's not like a whole bunch of things that say width, but then not anything that says height in the code. That kind of makes it look kind of erroneous. In the same way, if you saw a whole bunch of mallocs but no frees, or a whole bunch of frees and no mallocs, that would be like a warning. So right here, we're going to take this mapsan, right? So mapsan. And we have this y value, and we have an x value. So we got to think, well, what are we doing here? We're taking the global tx, global ty, and this is supposed to be a pointer, is it not? Yeah, we see glow tx, glow ty. We're trying to get that Glock pix, so we need to do and we got to wrap it like that. Glow tx, glow ty, right? So we're going to get these values. And right now we could set it to some type of trap, like 0 minus, I don't know, 70707, like that. Sure, that's a new trap value. And that's still within the range of 32,000, isn't it? Oh, it's not. That is out of range for a 16-bit value, especially a 16-bit sign value. So if we want to be kind of safe about that, we need to remove one of these. So, I don't know. Let's just call it 7007. How about that? 7007. That's in range. Okay, now that we're looking at this, let's kind of continue this. So we have the tx, so the x value goes over here, because it's the remainder, and the y value goes in here in the formula, obviously, because it's our snippet, and we know our snippet works. But we also want to think about it, right? Every time we use our snippet, we don't want to just blindly use it. We also want to logically check it and make sure that it's correct. And that redundancy will further help us from making mistakes. This integer value, how do we want to do that? We just want to call it, I got global tx, global ty. How about glodex, right? I16 and call it glodex. And how about, you know, I don't know, 909? Why not, you know, 707, 808, 909? I don't know, it doesn't really matter. We can make, you know, at trap value. Okay, so global index right here. Okay, now we have a global index. This global index is in terms of pixels. Okay, so really, if we want to think about it, it's a global. This is the global index, and then we're going to need global component. Okay, a global component as well. Let's take all this and kind of move this down a bit and change our trap values a bit. So 6, 7, 8, 9. So global index, global component, and the global component equals the global index times 4, right? And we can make a note of that. 4 is RGBA, right? If you want to know, like, what's that 4 about, right? It's 4-byte color, RGB and A, okay? Okay. Now, what's the next thing we want to do here? Glodex times 4, global component. Convert pixel xy to index. So that's all we did. This section is done. If we want to concentrate on the bit packing stuff, this is a put. Oh boy, this is going to get serious, isn't it? So how are we going to effectively kind of take this 32-bit integer and yeah, how are we going to do this? We have everything in a byte array. So does it make sense to have a branch for if it's within the range of the red, if the range of the blue, range of the green? That would probably be the easiest way to do it. And I'm all for the easiest way. I think the easiest way would be that. I don't know if it's the most efficient way, but the easiest way, I think. I could be wrong. Maybe shifting over, right? Maybe merging everything together, but then we have to put it back, right? Because we have to edit these values. So I think, so because we've partitioned it like this, right? Everything kind of fits nicely in R, G, B, or A, right? And we can see which indexes correspond to what things here, right? And so we know that, so why not do that? So we have this offset dex, right? And let's do bit packing stuff. I'm just going to call it bit packing stuff. I don't really have a good category name for this. Okay, bit packing stuff. What are we going to do? How about switch on OSDEX. And we're going to have some cases. We're going to have case Um, I believe we can do, instead of cases like case 1, can we do a case with a comparison? Or is that not a thing? Can we do, hold on. Case with logical comparison switch C99. Like, is that something that's allowed? Because I think it only needs a constant, but I don't know if a less than, I don't know if a relationship, a relational operator, that, I don't know if that counts as a constant expression, you know? So like this, can we do this? No, you cannot. Now, is this... This seems pretty restrictive, so I would automatically assume that this language is C. Interesting. So this is like a... Okay, now I'm getting distracted. I shouldn't be trying to comprehend this. So Mark 65, condensing these. So each one of these cases is basically marks times 10, right? And it's a fall through. So 40. If it hits 4. Oh no, there's no fall through here. Let's see, where's 40? So it's because the integer math truncates. Well, it already says it works this way. I don't think they need another explanation. Unfortunately, no. Okay, so we can't really use a case for that. That's okay. So, you know, if osdex is and osdex, right? So if it's this, it is the alpha byte. And this diagram would be kind of nice if we can... I don't think this is going to fit. Well, actually it might, so let's take this. Can we take a copy of this and just shove it in here? We might be able to shove it in here, yeah? And this is osdex here. Can you just put this on the other side? Be like, hey, osdex is over here. I'm gonna just say, this right here is a copy of diagram, and then just do dia P5D main, right? That's from file paint5d.data. But we can just kind of reference this diagram right here. I think it might be important to kind of be able to look at this diagram as you are writing the code. Because of the index for the OSDEX, the bit packing is kind of maybe inverted differently than you kind of think it is. So I think for the bit packing stuff, it might make sense to have this diagram here. We could remove it if we wanted to, but I think maybe having it right here might be nice. Right, so let's just kind of like do everything here. So alpha, red, green, and blue, and in the inverted order, right? So 1, 2, 3, 4, and then else, air out of range, I guess, my man and my dude. Okay, so 0 to 3, and we can see 0 to 3 in the diagram. So 0 to 3 in the diagram, 4 to 7, 4 to 7, then 8 to 11, 8 to 11, and then we see 12 to 15. So instead of doing a switch statement, it might make more sense, it might be faster to just pack everything into a 32-bit integer, and then just do the correct offsets, and then unpack everything. Like, that might actually be faster, even though we have to access more memory. I don't know. I don't know what would be faster, right? Less branching, but more memory access. I think memory access is a lot slower than computational logic, though. And therefore, it's going to be faster to add these branches. So 0, 3, 4, 7, 8, 11, 12, 15, etc. Okay, and let's space this out a bit, just so that everything kind of lines up, but we still get our numbers to highlight correctly. Okay, cool. So this is alpha right here. This over here is the blue. This over here is the green, according to our diagram. And this last one is our This last one is our red. Okay, and since we've already let's kind of use that extra space to our advantage and get right up next to that column limit. Okay, alpha, blue, green, red. And if that, does that backwards make RGBA? RGBA, yep, okay, cool. The component index is the red byte. So red, green, blue, right? Red, no offset. So we're going to take the glowcom, and we're going to take, well, let's get the actual data, right? So now we're going to actually do PAINT5D here. Or not PAINT5D, but PixName has the data we need. So it's this allocation right here. And this is kind of big here. So I think what makes sense is if we say, define pix, and we call PixName, right? So PixName CPU pixels. Maybe we want to call it CPU pixels. Like that, right? Saying that, it's on the CPU. I mean, maybe it's a little bit longer, but I think that maybe that could be useful. Or not useful, but I don't know. I like it. If it gets to be too long column-wise, then we'll use something different. But right now, it's just with the mental indirection here, right? These are identical matches, and it's just taking off of all of the name spacing, right? So we're going to do CPU pixels, and then we're going to do this global component. So this glowcom, and this is going to be alpha. And if we look at alpha, or alpha in our diagram, right? Alpha in our diagram is 0, 1, 2, 3. It says it's a 3 offset here, right? So we might want to say that the it's I don't know, pix U32 we could call it. Backwards use U32 pix. Okay, well if that's what we call it. But is that a single pixel, or is that U32 pix means? Because it might actually mean a collection of pixels. A collection of pixels plural. So that's a plural thing. And what we really have is, first of all, it's not a U32, it's a byte. So we're wrong already. And why not just call it, you know, var U08, right? It's a variable, it's a U08, right? So var U08, is that a thing? Well, it's going to be now. We're going to call it, it's a variable. A variable is general to specific, right? So we want to make everything in a general specific to specific form. And I would say a variable is a very general concept. The number of bits in a variable is more of a specific thing, right? So hold on, I think my notepad is crashing here on me. Okay, so if we type this, then we just want confirmation that, yeah, that's a thing, hooray! If we type something similar, like with a dash, or like that, then we also want to type it correctly. If you do it backwards, we want to notify, nope, you're backwards. Backwards, use var U08 and general to specific. Right, so a little note of, like, why is it that way? Well, it's that way because it's general to specific. And what does var U08 actually stand for? So, var U08 means, var U08 means, var U08 means. Okay, so, okay. So if we type this, we'll do this to recognize the word we just spelled, and then say variable uint 8 bytes. Or, ooh, not 8 bytes. Jeez, that would be bad. That would be very erroneous, right? So let's not do that. Okay. So we just made note of that, because we made a new variable name. So we just want to be consistent here and have... so then in here, right, it's going to count down, or count backwards, right, all the way back to 0. So this is going to be 2. And then over here, it's going to be the same thing, but this is going to be 1. And then this is going to be 0. And is that correct, or are we offsetting the wrong way here? Red is 0, offset. This is the next byte, the next byte, and the next byte. 0, 1, 2, and 3. Okay, that is correct. This var U08 needs to be defined up here. So right here, we're declaring our variables. Let's do a U08, var U08, and this equals, I don't know what we want to call it. We could do, I don't know, 99. Doesn't really matter. It doesn't really matter in the sense that it's not going to be useful to us. It's not going to be useful to us, but whatever. We'll put it there just in case. I don't think it's going to end up useful, but we use trap values on everything else, so we might as well be consistent. Okay, so we have this global component thing. How are we doing this bit packing? So we have the 8 bits we want to work with, and we want to get a local value out of this. So, we could say offset local, I guess, would make sense. So let's say for OSTEX over here, let's say U08 OS lock, or offset local index, oslid local index, or oslin local index, local index, oslid or oslin, or local oslin or oslid. Well, let's just look it up on Google and see if those are any names of anythings. And god damn it, fucking Windows, man. Yeah, the shaky thing is kind of stupid. So let's do oslid and see if that's a thing, and then we'll do oslin. Lifting the lid on third-party inducement grid, oslid something something. Images. I don't know. We get some patents here, but not much stuff. Okay, so we got oslid. How about oslin? Oslin, is that a thing? Looks like it's a person, I guess. Probably, yeah. What the hell? And of no good options. Now we're getting sidetracked. But the idea is, I was gonna put this. I'll just name this nuclear baby in my shortcuts. We'll come back to it later. Nuclear baby. Okay, anyways, where were we? So oslin, what about when we go to, instead of images, what if we do all? Michael Oslin. Okay, so it is some type of person. And what kind of person are they? Research fellow. National security. And director of Japanese studies at the American Enterprise Institute. Uh-huh. Interesting. Interesting. So, slightly politically charged, which I don't like. I do like that he has a background in, Japanese studies, because I do like Japanese. Japanese kanji, even though I don't really know much about it. I know a lot about, what different kanji mean, but, I can't speak Japanese or anything, right? I just dabble in it. So oslid would be less, local index. Well, if it's index, I and D for index, that's kind of separated. It shouldn't be like lin. Oh, that's where we're in, local index. What about, how about oslock? Right? Offset local. But offset local could be like something else, I think. Let's make sure that, let's kind of look through our shortcuts and see, do we have an oslock? And does it have a reason? So we see osloci. Oslock index. Interesting. So we already have something like a oslock index. And Okay, so in my shortcuts, I do have something called os loci, but there's no os lock. So here's what we're gonna do. We're gonna go into our shortcuts. I say oslock is a good enough thing. We're offset local. And offset is oslock. We're gonna assume that when we say oslock, that we mean a local index, right? Because there's no x, there's no y component. So oslock. Okay, we're gonna assume that's a local index. Oslock, and if you do it backwards, lockos. I want to make sure that's nothing. Lockos, like locus in genetics. Lockos. I don't know much about genetics. I just know random things sometimes. So backwards, use oslock. And what does lockos mean? So lockos means and lockos means. So lockos is local offset index. So we're going to say it has a generic meaning besides that. So the exact meaning, we're going to say, it's a local offset index, but besides that, it's generic, right? I mean, it's still pretty specific, but in terms of, it's generic in the terms of the diagram that it applies to. Okay. So we'll do oslock. And I don't know. 23. Okay. So oslock is going to be that local index. So we have the variable, and then we have oslock equals, well, it's between 0 and 3 already. So it's going to be osdex minus, guess what? 0. And then everything else, that first number, right? That first number tells us what we need to reset to, right? Because we're going to 0 everything out. So it's between 4 and 7, 0 that out. Between 8 and 11, 0 that out, right? So keep on zeroing everything out. And then over here, same thing, keep on zeroing everything out. So this 12 minus 12. So this matches, this matches, this matches, this matches. Okay. So the local offset is the kind of input offset, and we're zeroing it out, right? So minus whatever that is there. So we might, I might just say, well, first of all, this is ugly. Like, that alignment is horrible. We could, if we really wanted to, we could kind of put these minuses over here if we wanted to. Even though these are different things, but at least you can see the... Yeah, these are different things. They're not related, so maybe we shouldn't willy-nilly align those together when they're not related at all. I think that is actually going to be a problem here. Let's not do that. I changed my mind. Sometimes alignment is a bad idea if you're trying to make it look like things are related that actually aren't related. So let's not do that. Okay, so we got this 0, 1, 2, 3, and then 0, 3, 0. So we could go 3, 0, 0, 7, 4, 4, 11, 8, 8, 15, 12, 12, right? There's an obvious pattern there. So that's good. Okay. So what's next? Well, now that we have a local index into these bytes, we know that when we're bit shifting, it's going to be like bit shift by this osdex, by the os locate lock times 2, because right, everything's in a cluster of 2. But which way do we have to shift? Well, we have to shift it out. We got to shift it out. We got to shift it to the right. And like right, so if we are at the first one is 0, so this we shift 0 to the right, and we still get this. We shift 1, we shift 2, or we shift 3, right? Oslock should be in that kind of range. So I'm thinking that now we can go into a more generic piece of code and say, assert that, oslock is less than or equal to 3 or 4. 1, 2, 3, or 4. So 0, 1, 2, and 3. So it's between 0 and 3, right? So less than or equal to 3, and that's because 0, it's 0 or 1 or 2 or 3, right? That is why we have that assert like that. Okay, so to get the actual bit value, and are we just getting the bit value, or are we kind of modifying it? So this is the put. So in order to put this, we're going to have to shift that in there. Okay. So to shift that in there, we got to shift over to the right, because the indices, right, are shifting to the... Sorry, did I say the right? To the left. Because 1, 2, 3, 4, or 0, 1, 2, 3. All right, we shift over to the left. So we're going to take the value, and the value absolutely needs to be in the correct range, or this math will not work at all. So looking at this, we got this tile value. And do we have any asserts for these ranges? No, we don't have any asserts on these ranges. We should probably do some asserts on these ranges. So let's do bounds check inputs right over here. Okay, we need to do 10 more push-ups according to our timer. So we should get on that. Bounds check inputs. And let's just do it, right? So there's a lot of asserts here we can do. So assert that, till qua is less than or equal to 0, 1, 2. Okay. We're going to assert that the tile exponent is less than or equal to 7. Assert that the tile layer is less than or equal to 2 as well. 0, 1, and 2. Yeah, the layer is 0, 1, and 2. This quadrant here, I got the quadrant wrong. The quadrant, there's actually 4 of these. So 0, 1, 2, and 3. So this is actually a 3 here. And assert that the local tx is, depending on what the tile exponent size is, this could change, but we absolutely know it's less than or equal to 255, though its valid range could be even less depending on what the tile exponent is. But that's good for now. We can add some more robustness to that later. And we want to assert that the offset dex is less than or equal to 15, right? Because it's 0 to 16. Or sorry, it's 16 values, which is 0 to 15. And we want to assert that the tile value is less than or equal to 3. And 3 is, right, we said that there's 0, or 1, or 2, or, well, this doesn't really help us, does it? Well, here, what really would help us is if we look at the bit pattern. So we have enough room here where we can do the bit pattern. So, 0, 0, how are we going to align that? So 0, 0, or 0, 1, or 1, 0, or 1, 1, right? So if we're looking at the binary representation of what's going on there, that is why we have the 3, right? If we want like a quick reference to, well, why? Why is it that way? Well, that's why, right? So we're going to have to just understand that this is down here, that this is binary, and that this is decimal, right? You're just going to have to be able to look at that comma and be like, oh, I get it. Otherwise, you know, I can't help you. We're kind of going pretty low level here. So I'm going to assume that you know what that is, right? So hopefully that's obvious enough. So let's just do a little thing here that, you know, let's do a at vid IID. So let's say just in case we don't know what that means in the future, let's just do 0072, and the time is 3 hours, 7 minutes, and 30 seconds, and Tilval commentary is the decimal and binary representation of its values. Okay, so that's what that is. Yep. So right down here, right, we're talking about tile value, we're talking about this last thing, we're talking about those comments right there. Okay, so the next thing is, should we look at the range for the exponent, or are we good enough to where we don't have to worry about that? Let's just do some mindless exponent check anyway. So if the 0 equals the tile exponent, we're gonna assert that. Actually, we need two asserts, don't we? Assert loc tx is less than or equal to 255, right? So same assert as previous. And then else, and then we're going to paste this. Here's 1, here's 2, here's 3, here's 4, here's 5, here's 6, and here's 7, right? So that is like, maybe we shouldn't do that. Maybe this needs to be in its own function. Maybe this is out of control right now, right? It's good to get a feel for, like, this is kind of like, I don't know about this. I don't know about running this all the time like this. This seems kind of, you know. So, here's what we're going to do. We're going to throw this in here, and we're just going to say, you know, if, and in our PAINT5D data, or not, this isn't PAINT5D data. In PAINT5D data, we should have like some defines or something already. Let's see what kind of defines we have. PAINT5D data and then debug variables. AAC 2020, actually define AAC 2020 PAINT5D bound check inputs. Okay, so a little macro for bounding checking the inputs, and if this is greater than or equal to 1, then we're gonna be like, yeah, let's go, let's do this, right? And we'll put this kind of macro right at the end of the section as well. So, you know, we'll do an end if, and then we can make a note of what this is, right? How did we do that? We kind of did like a little hashtaggy thing. I don't know. Something like that to guard this, because this is gonna get, this is a little bit ridiculous, right? So we have this kind of 255. It's gonna be easier if we just think of it as 256 minus 1 for these, because then the other things are just gonna be easier to do, right? If we do it like that. So let's actually do that, and let's just repaste. No, we already kind of did the found and replaced some other stuff. So let's kind of. Okay, now, let's take a look at this and be like, okay, 256, 128. Okay, how about this? 64? Yep, 64. Okay, how about this? 32. 32. How about this? 16. 16. How about this one? Well, after that's 8, right? And after this is 4. And after this is 2. Whoa, hold on here. 0, 1, 2, 3, 4, 5, 6, 7. What are we missing here? Why is that? Why does that not seem correct? We got this tile exponent. And if we're looking at this... Okay, why it doesn't look right is because it's not right. Right, the local value is in this 128 to 128. It's not within this 256 to 256. For the level map data, we're probably going to use this kind of pattern. But for what we're looking at right now, this actually needs to be split up. So 1, 2, 3. Paste this down here. Bam. 1 minus 1. Whoa, hold up there. Yeah, because it's, 1 minus 1, it's 0, right? It's one gigantic tile that covers the entire canvas, and that's actually what we want. So that makes sense. So 128, 64, 32, 16, right, all the way down to 1. Okay, cool. So we got all these crazy asserts for the x's and y's. A little bit overboard, but since it is overboard, we added a little macro here. Right, we don't want to make it easy to shut off debug for everything, but, you know, in some cases, we might want to, you know, put stuff in there, right? Make it easy to optimize. Okay, cool. So PAINT5D put, we got the bounds check inputs, and then down here, we know that we don't have to worry too much about this location here. It should already be within bounds. This variable, that's good. Okay. So what are we doing now? We are taking this variable and we're trying to inject something into it, right? We're in the put. We're trying to take this tile value, which is two bits. 0, 1, 2, or 3. We're trying to take that tile value and we're gonna shove it into what we have already. So we're gonna take this tile value and we're gonna bit shift it over so that it fits into the let's close these. Oh, we can keep that one open. What diagram? We want to shift it over. This is why it didn't make much sense to paste this diagram, because now we got to scroll up and down, but we can just look over here at it. We have these bytes. We want to shift over by 2 times whatever that local index is. Okay, so we're going to take the offset local. There's going to be 0, 1, 2, or 3. We're going to multiply it by 2, and we're going to shift over. And are we shifting in the right way? Yeah, because we want to take this value and we want to put it into the location it needs to be inserted into the current byte, right? So, so this is in position. After it is in position, we want to do some bitwise ORing to merge it, right? So, slide delta bits into position. Okay. The other thing we want to do is we want to erase the bits we're about to OR with, right? So we have a previous value, right? We have this var U08 here. And this is the previous value in that slot that we're about to modify. So we want to take that value and we want to clear those bits that we're about to overwrite. We're about to OR them. To do that, what do we need to do here? We need to make a mask where everything is... We need to AND it with a mask where everything's Fs. I don't know. See, I don't do much of this, so it's going to take me a little bit of time to figure this out. So I think we need to, like, AND it with something. And we're going to AND it with... we want something knotted, really, don't we? I want to shift over like a... So we want to take, like, 0xFF. Or, hold on, do we even want to FF? That's a whole byte. We don't want a whole byte, do we? We want, like, we want this... It's a cluster of 3, right? It's 0, 1, 2, and 3. So we want those 2 bits. So we want... So we want... In this section here, for this bit packing stuff, let's create something called define bin. In the binary is 0, 1, 1. And it's 3, right? So 2 set bits in a row, right? That's what that is. Let's absolutely make sure that's correct. So let's open up a calculator and make absolutely sure that is correct. I'm fairly certain, but it's like this bit shifting stuff you can easily do it wrong. So let's just look at little bits. Let's do 2 bits. We're expecting a 3. Yep, simple stuff. Okay, so bin 0, 1, 1. And then down here we can undef bin 0, 0, 1. Undef bin 0, 1, 1. It's just going to be easier if we know what we're looking at. It's binary. So this is binary. We're going to take it, and we're going to shift it over into the oslock times 2, right? We're going to shift it over where it needs to be. And then we're going to... we really don't want to do this. We want to XOR it. So let's see if we can flip all the bits. Right, we want to take this. We want to take this thing. We want to shift it over, and then once we've shifted over into the spot, we actually want to flip that. So I forgot what that is in C because I rarely use it. I have written thousands and thousands of lines of code so far, and I have yet to need to use it, but now I need to use it. So invert bits C. So that I think it's like the tilde, but I don't know. Yeah, I think it's the tilde. How to use this tilde operator. Yeah, so I think it's tilde. This is, okay, Boolean inversion. Okay, and tilde operator, however, does bitwise inversion, where every bit in the value is replaced with the inverse. Okay, yeah, so it's tilde. It's tilde. I remembered correctly, but, you know, I wasn't sure. This is getting way too... So we want to take this, and we want to invert all the bits, and then we AND it with the variable, right? We invert all the bits, so erase everything in here except the thing we want to replace it with, right? That's why you have this oslock times 2. And we might want to make sure that we don't accidentally do anything wrong, so we'll do it like that. Tile value. Okay, so we have the original variable. We're going to blank out the bits that we want to replace, right? So 2 times oslock, shift it over to the left. And once we shift that bit pattern over, that's the mask. We want to invert it so that this is all zeros, so that when we AND it, it deletes those bits. Okay, so that should be what we need for this. Now, I'm going to explain this again because we're going to need some video timestamps to do video timestamp. I'm going to explain it again one more time after I'm done writing it. Okay, so we have, this is in the new bits, this is the current bits, and right, everything's 0 filled, so we take the bits, we slide them into position, everything else is 0. Here, everything is something, except for where we want to, except we zeroed out where we want to replace it, right? So we have complementary patterns, right, where we have, like, conceptually we have something like this, where we have, like, you know, conceptually, this is what we have. Conceptually, this is what we have. And then conceptually, what we have over here is, right, we're taking that tile value and we're blanking, we're just shifting the value into position. So we're taking this tile value that we want to add, and we're shifting it into position. So conceptually, what we have here is the inverse of this, right? We're saying that if the tile value is 3 right here, right, then conceptually, this is what we have. Conceptually, we have something like this, where if oslock equals 0, 1, and 2. So if oslock equals 2, so conceptually, if oslock equals 2. So just make a note that it's conceptual if oslock equals 2. So let's think about it. 2 times 2 is 4, right? So we have this over here, and we're going to shift 1, then shift 2, then shift 3, and then shift 4, right? Same thing here. We have this cluster here. We're going to shift over 1, and then we're going to shift over 2, then we shift over 3, and then we shift over 4, right? So, because oslock equals 2, 2 times 2 is 4, right? Okay, so that makes sense. So now that we have these, how do we merge these together? Well, if we merge them together, we have to do OR. So the bitwise is saying, if this or this, we're going to make it true, right? And so this is going to, so these ones, this data here is going to overwrite this, right? And this data here is going to overwrite this, and this data over here is going to overwrite this if we use an OR, right? So we want to make sure that we use, oh god, and I always do this, and we don't get warnings for this either. So we need to make absolutely sure we don't use the wrong operator here. That was the wrong operator. I got burned pretty bad last time I did this the wrong way. So, and then we need a bitwise OR. So we'll take a bitwise OR, we'll just shove it right there. And after we have that, we need to just say, well, what is this? I guess this is, technically this is our new var UO8, right? So we could just say, if we wanted to, we got this CPU picks, glowcom, etc. I think that this needs to be extracted to a variable, because we're doing all this stuff over here, in here, but if this was outside of a big switch statement, then we could actually, well, let's extract what we can. So the global component index plus the correct offset. So, I guess we could call it the byte index. So I'm going to call it bydex. So this is the component index. And I call this, Videx. Is that really what we're going to call it? Or is this, are we doing this properly? Hold on. So this global component is figuring out what byte we're looking at, right? So what the hell is this? Does this make sense? Yeah, because it's the first component of the pixel, right? So together, all these different offsets of the different pixel, right? Global component index, okay. And really, I'm just gonna call it Rdex. I'm just gonna call it Rdex. Because it's actually indexer into an array, that's why I'm calling it Rdex. And we can say that Rdex equals right, like this. Rdex equals glocom plus 3. This is plus 2, plus 1, plus 0, right? And because we have that, we can, for this var UO8, we can do this outside of here. And this minus 12, I mean, we could do it outside of here, but let's not. Let's just say Rdex equals this CPU pix, right? So we know it's index accessor into here. I mean, that's fine. It's a little bit redundant, but let's not worry about the redundancies yet, right? Where we could make it more compact. Let's not worry about compactness. Let's worry about it being kind of just straightforward, right? So less than or equal to 3. So I'm seeing a problem here. Y is 0, 1, 2, 3. So that makes sense. Why don't these numbers match? Oh, right, because these are indices. They have nothing to do with this. Those numbers are different. So I think what might make sense is something like this. So the Ostex 0, 3, because then we can actually see, if we do it this way, then we can see 0, 3, 4, 7, right? And we can see the counting, and we don't mistakenly look at certain numbers and be like, hey, I thought those numbers go together, but they don't, you know? So I think I like it like this better. So I like the and over here, I think. Yeah, let's break it apart like that, just because I'm making connections that aren't actually there with these numbers. So let's kind of break it apart so that we look at these numbers here and we don't associate these numbers, right? Because these are totally different, right? This kitty corner thing here, these 8s, these 12s, these 4s, these 0s, they are related. Okay, so that's a little bit better. So we have this array index, right? And what are we going to use that array index? We're going to use that to put the data back where it belongs, right? So I'm going to take this var, that, and in PAINT5D, we could actually take, do we want to just take we could just use CPU pix again. Let's just do that. Let's be consistent. So CPU pix, and then Rdex, and then equals this crazy bit shift stuff, right? So bam! There, we've put it, right? We've put the stuff where it belongs. Excellent. Done, right? 2D video timestamp, so we're not quite done. Okay. So, and we have this little OR here. So, you know, we might want to make a note here. You know, bitwise OR to merge together. So that's a bitwise OR to merge together. The AND is, why do we have an AND? This, because we're taking this 3, or we're taking these 2 bits, we're shifting them over into the location we want to erase, and then we're inverting it. And once we invert it, then when we do an AND, where both bits need to be true, it's going to leave a hole here, right? Because there were zeros here, right? And it'll leave the bit patterns on the sides intact. Okay, cool. So that makes sense. Okay, so that all makes sense, and this is really what we need here. And that's literally the whole thing, right? So we got these maybes. If the tile value is set down was different than it was previously, maybe we should return a 1 to signify that. Yeah, I mean, maybe that could be useful. Right now we're just going to return this. This vital to do, we can remove this vital to do though, because that is no longer a thing. How hard would it be to implement this? Is the data already there for us to use? Because if it's already there for us to use, then sure. But if it's not, then I don't really want to. And I see that it's not really there for us. We would have to shift it out, right? We're overwriting that spot. But if we wanted to get at it, we would have to actually shift it out. So we'd actually need another step up here to determine that. It wouldn't be too hard, though, now, would it? Sure, like, if we did that, here. So it would be something like this. Why not finish this? So, say that, you know, if, or, so this var uo8 here is our variable. Where are you? So this variable, where does it get assigned? So it gets assigned from CPU pix. So it's the variable that we're dealing with. It's from the pixel data. If we shift that over by os lock times 2, right? Shift it over in the other direction to unshift it out. And then we take this and we have to mask it, right? We gotta mask it because it's only a 2-bit value, right? So, so this is tile value. We could call it, we want general to specific. So, is it tile value previous because it's more general, or is it more specific to say, well, in our test code we do actual whatever, expected whatever. So we could say, you know, old till val is equal to this, right? We're going to shift it over like this, and then we're going to mask it with the bin 001, right? That is how we would get the old value. And let's just call it old val, right? Old val equals shift over in the opposite direction, so right shift instead of left shift, shift it out to put it in the least significant bit position, mask it with the and bin 001, and where are you, bin 001? I see you here, but then it's not, oh, bin 011, right, because it's 2 bits in a row, okay? And that's how we get old val, right? And, you know, if, so with old val, what we could do is, you can just say return if tile value is not equal to old val. If the tile value set down was different than it previous was, we should return a 1 to signify that. So yeah, tile value not equal to old val, right? So if we say the tile value and the old value, if they're not equal to each other, they're different, then we're going to return a 1, right? So let's get rid of this right here. And there. Ooh, look, we implemented that thing, right? That simple thing we're like, maybe we should do that. Wasn't too hard, so might as well. Since it's going to be harder to implement later than right now because we're in the current headspace, you know? So if it's a little tiny feature where it's not too hard to implement it and we're like, maybe we need it, then I will kind of give into that violation of Yagni. Yagni being you aren't going to need it. Okay, so with this old val, let's go back up here and say, oh, well, where is that going to be? Where are we going to put that? Well, how about this? This is the cert section. What am I doing? I'm in the wrong section. Bounds checks, and then we'll just call this U08 old val. And it's, I don't know, I just set it to 0, I guess. I really don't care. Previous tile value. And tile value is up here, right? Tile value is up there, cool. So old value. Old value we shifted out once we get the variable from the pixel array. Or the byte array, whatever you want to call it. And we want to mask it to make sure we're just getting the value. Okay, so right here, so yeah, let's do a little kind of video timestamp of what's going on here, because this is obviously kind of complicated. So let's actually document what's going on here. So at vid iid 0072, we're going to have to do like 20 more of each thing. So vid ID is 72, and the time is 3 hours, 38 minutes, and, I don't know, let's say 10 seconds. 10 seconds might have been too much. Okay. So in the section below, we're doing the crazy bit shifting we need to do to load the changed bits into position within the byte array that represents the array of pixels for the PAINT5D system. So that is kind of a mouthful. And also, this does not belong inside a comment. That would be kind of bad. Okay. So let's make a commentary here. Bit packing logic to only change the bits where the new value needs to be stored. We need to erase the bits in the proper position by masking we need to erase the bits in the proper position by masking. Then merge the bits together by using a bitwise OR, right? So one of these guys. And by masking, so that's going to be an AND. Okay, cool. Okay, so let's explain this one more time. This is just for the feature of knowing if the value we put is actually different than the previous. So tile value not equal to old value will return a 1 if they're different. To get that old value, all we got to do is take the local offset location. Yeah, oslock. I can see why lock is kind of a bad idea, because lock could be like location as well as local, but this stands for the local, offset local, multiplied by 2, right? And we're going to shift that over and this is going to zero it out. It's going to put it all the way to the least significant bit position, and then we mask it off with 2 bits, and then we get that 2-bit value that we can compare with the previous value. Right? Well, this is the previous value, and we can compare it against the current value, which is the tile value that we inputted into the function. Okay, so here's the thing we really care about, is right here. This is our array of pixels, but the pixels are stored as bytes of R, G, B, and A. This array index is the actual index to the current component we want to look at. So we might want to look at the alpha component, the blue component, the green component, or the red component. So in order to get there, we have to take this glowcom, which is going to give us the first component of the pixel, right? So we take the pixel index right here, we multiply by 4, and that's how we're going to get that global component. So this global component is always going to be the red byte of our pixel. So since it's the red byte of our pixel, we see this is red, we see the offset is 0. To get to green, 1, blue, 2, alpha 3, right? We have to offset like that to get the correct component. So here's how we're going to get the actual byte we're looking at. Here is the actual byte we're looking at. But we have to, this is where we're reading it, but we also have to put it back, so that's why you have to keep track of this variable. And here's the local offset location, which is going to help us with our bit shifting math. And we can see a diagram over in PAINT5D right here to help us. We also cut and pasted that diagram up here. So let's go back down here and look at this formula one more time, because we haven't explained it all. So conceptually, we're kind of like taking a bit pattern here, and if oslock equals 2, we would be zeroing out these bits of the byte, and then we want to do the inverted thing here. So for the tile value, you want to take those bits, and we want to shift the tile value bits directly into position here so that they can go slide in right there over those zeros, right? So we take a bit pattern of all ones, of 2 ones in a row, 2 binary ones, we shift it over into its correct location, okay? Once we've done that, we want to invert all the bits, right? So before this, it would look like this, right? Originally it looked like this, right? Because we took a binary 1-1 pattern, shifted it over, and that would give us something that looks like this, but then we invert all the bits to get something like this, right? With this bitwise inversion here. Okay, so now if we mask the variable value taken from the bit array with this pattern, it's only going to leave everything except the thing we want to overwrite. So it's going to erase the part we want to overwrite with this data right here, right? And to merge these two things together, we're going to use this bitwise OR here. So to get the thing we want to merge, we got to put it in the correct spot over here. So to put it in the correct spot, we shift it over by the exact same amount, right? So we see this shifted over this amount, and this is also shifted over this amount, which makes sense. And we're going to shift over the tile value. Now the tile value should be between 0 and 3. And if we bounce check it, we can see we should have a bounce check somewhere here. Yeah, it's less than or equal to 3, right? Because the binary patterns for 0, 1, 2, and 3 are right here. So those are the bit patterns. And so that looks good to me. I think we've done that correctly. Also, we want to make sure that we don't mistake logical for bitwise, because the calculations will let us put logical things where we need a bitwise things. So this needs to be one AND symbol, and this needs to be one OR symbol. And if you do that wrong, you're going to be in a world of pain, because the compiler is not going to warn you about it. So there we go, that's the explanation. So let's kind of do a @vid IID of the end of the explanation, because it was kind of long, right? So 46 minutes and 9 seconds. And this is the end, and this is the beginning, right? So the beginning and end of those explanations right there. Awesome, cool. Okay, I think we're done there. I think that looks good. I am kind of scared. There's a lot of code that we've written, a lot of very complicated stuff where it's like, oh god, this is completely batshit crazy. But this is what we get for trying to do what we're doing, I guess. Let's give it a roll and see what's going on here, and then after we've solved some type of rudimentary problem, we'll try to, I don't know, do some push-ups. Unknown type, UO8, so really simple problem to fix. So we wrote all this code, but we don't have any macros here. So we have UO8, do we have an I16? I'm sure we have an I16 somewhere. UO8 and I16, and what else do we have? Oh, also this thing, did we undef this? Okay, we did, okay, cool. Yeah, so the only thing we need to do is that I16. Also, there's this gibberish here, so we didn't finish that. So let's kind of get to where it kind of shows us this gibberish, even though we should probably do something more than that, because it's kind of a hackish thing, but we were like all over the place, and we wanted to get something down as quickly as possible. So, define UO8, define I16, and then let's just make a little checksum. It's only 2 things, but out of habit, I kind of like doing this. Then we'll take these defines and we'll undefine them down at the bottom of the section that encompasses both the get and put functions. So just write undef here. Add a space. Okay, so let's give that a shot. It's not going to work because we know this is going to happen eventually, but we want to get to that point where that's what's giving us trouble. And we see comparison is always true due to limited range of blah, blah, blah. Okay, yeah, I know what that's about. Let's go to 833 and fix that. And we're not going to fix it by getting rid of it. So local tile x less than or equal to 255, right? Because it's in this range here. We want to make sure that if this changes... Right, if this changes number of bits and it gets more bits, I want to make sure that we still catch this, right? So we're going to do something hackish. So we're already in an inefficient section, but let's just do like an int32, right? Let's give it the most bits that we'll probably ever use in this system here. And that is going to end up kind of ugly, isn't it? Whatever. I mean, let's put offset and tile value here like this. Actually, I don't know, man. The tile value is really what... Yeah, logically, these kind of need to be grouped. Like, these two are kind of different than these things. So let's kind of group it like that. And the int32 cast. And then also, after we int32 cast it, we have to do something else. You gotta like +0, and then we're gonna wrap it again. And this is just a way to subvert the compiler to not warn us about it, because we actually want to, in case this type changes size, I don't want to, like, maybe it'll never change size, but we're in a debug block anyways, so I'm not worried about efficiency. So this is just in case we widen this type. We want to actually be able to catch it, right? So let's give that a run and see if we've successfully subverted it. Oh, well, that's undeclared. So we actually have to do int32 now. So define I32. Okay, and then down on the bottom, we'll have to undef that, right? So we'll duplicate this line, change this to 3. And then undef I32, and then also fix this, because this is completely wrong. Okay, cool. Now let's give that a run, and see if we can eventually get to the spot where we kind of like... limited range of, yeah, limited range of that, limited range... Okay, so going back up here, there's still more things in our bounds check that it's like, you know, screw you, basically. If offset is greater than or equal to 0, or... Okay, so that's in our little switchy kind of statement, right? Like, down here. Greater than or equal to 0, and less than or equal to 3. That is kind of annoying, I have to say. So, we're just gonna say, you know... If, we're gonna say if 1... And we're just going to comment this out. We want to be able to see this pattern here, right? there's an obvious pattern that we want to see. Right, we want to make sure that offset is positive. That I'm getting tired here. Let's get this working, right? So there, we still got the pattern, but we commented that one, and you know this thing, right? Unexpected. We just don't know how to write code. That's what that is. So we see Glowcom, and we kind of lined it up with here, and I guess that's probably why we did it, because we were being stupid. But these array indexes should be this symbol here, right? Okay, cool. Okay, what other stupid mistakes have we been making? No air function. Okay, that's easy. So up at the top, let's define air, and it's going to be AAC 2020 PAINT5D, and then ERR, halt, my bad. Halt with the capital, camel case for functions. Even though it may not seem like I use camel case for functions, but I swear I do. It's just that first of all, the namespaces are very large, and very often the function name, if the function name is referencing a type that is inputted into it, I actually don't want to change the casing of the type. And variables are snake case, and so if a function references a lot of variables in its name, then the function starts to look like a variable because a lot of the camel case isn't there. And then abbreviations are all capital, so that's not camel case. So this is, yeah, yeah, I don't know, man. That's the way I do it. And we want to stick to this consistency because we finally found something that found a level of consistency in our code that's pretty good. Even though it's a little bit strange, but I like it, so let's give that a shot, see if that works, and see what the next mistake is. But we're trying to get to this mistake on 1030. Oh, cool, so there we are. And let's formalize the mistake here, right? So the mistake right here is, you know, error finish this. Error finish this code. So 2021 and hello, my friend. I don't know, whatever. Just some blah, blah, blah stuff. And for the get is actually going to be easier because the get is kind of like all the same logic we did, but it's just it's a lot of the same logic we did. Maybe not all, but okay. Finish this code. Hello, my friend. Cool. So let's try to get that getter done. Like, I'm kind of tired, but we're almost at 4 hours, so we'll do like 20 more push-ups and whatnot, and then we'll try to get that taken care of and finally have done a decent amount of work for today. So git bash here. Let's do a git status, git commit-am, or actually we gotta do a git add dot git status, git commit-am. To do now is it's still a broken commit, so let's comment that. Broken commit to do PAINT5D get. Okay. So what's next here? I don't know, my friend. I'm getting tired. So let's look at our like push-up counter thing, because we're about at 4 hours. We're close enough. So let's look at push-ups, and 4 plus 2 hours plus, right? That's about 4 hours now. We're at 4 plus. So if we're at 4 plus, and that's 8 hours. So we should be at 80, right? So 60, 70, 80, right? So that's our 20 extra that we need to do. So we're going to do the 20 extra push-ups that we need to do, and crunches and squats. And then we're going to hopefully finish that last function and then call it a day, right? Because we've added a lot of stuff, and holy crap, man. Let's just keep on going and try to get this. Like, you wouldn't think that mapping out data like this would be so complicated. But there has to be a reason no one's done what I've done before, right? Like, we have a very specific vision for what we're doing. So let's keep on chugging away here, because we have some interesting insights. And I'm really excited to get this working, but holy crap. Jesus, this is a lot of work. Okay, so yeah, I'll be back. I'm going to do my push-ups and stuff. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Squats. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay. Okay, so that makes 4 and 4, that makes 80. So, I gotta put my socks back on here. So, just 20 more before I hit my 100. And then I will have done a decent amount of coding for today. And all my push-ups, despite really not feeling super motivated. Like, I'm not feeling super motivated, but I'm getting stuff done. So this 60, 20 more. We're at 80, 4 and 4. We're matched up to kind of like for the streaming we've done 4 and 4, 8 hours. We got the 80. So if our goal is 100, then that kind of sets us up for like these 8-hour work for 10-hour work days, right? And everybody brags about 12-hour work days, but nobody talks about 10. So I feel like I'm in that middle ground where it's like I'm doing more than 8, but not enough to brag about it. So let's see. Let's keep on keeping on going here. So this math, what do we got to do for this? I mean, a lot of this should really be duplicated code, because all we got to do is extract and shift. So the code that identifies the old value here, if we take all of that, that'll literally be all the code we need. This is almost a cut and paste of this code is almost a cut plus paste of the puts code. The old val variable from the put code is what we want to return from this function via an output parameter. Okay, cool. So the cool thing is that this code is pretty much a cut and paste of the other code, right? Like most of the stuff, we got to access most of the same stuff. We just don't have to change anything, right? So we got to do a read, but we don't have to do an overwrite. And the put code is actually reading and overwriting by the nature of how we're, bit packing the pixels. So let's take care of this. Let's get rid of this. And we know that we kind of want to just copy paste everything. So let's take all this stuff, and then we'll figure out what we need to kind of whittle down, right? Because, so this diagram here, I'm going to say, this diagram here, I think this is just kind of, if we're cutting and pasting this again, this is just going to get annoying. And it's not that helpful here. So I just want to say, instead of saying copy of diagram, we're going to just say, C diagram from file, and we could align that nicely like that. Okay. So something like that. And I don't know why we want to, should really align that like that. Okay, so let's scroll back up, and we're gonna let's fix up the formatting a little bit as we go through here. Yeah, so we want to take all of these, don't we? And so since we're so regular about how we write our code and how we have our variable names, it's not going to be too hard to do this, right? Because all the variable names we're using are pretty much the same, right? So copy that, and we're going to just paste that in there. So boom, paste that in there. And now the hard part is like knowing where we are. Like we could accidentally edit this get function. We could accidentally edit the put function thinking we're in the get, or accidentally edit the get thinking we're in the put, and that would suck, right? So let's hope we don't do that. And also, let's remember this tile value here is a pointer, right? This tile value is a pointer, and therefore this thing doesn't make any more sense. So actually, let's look at the tile value, right? Because it's a pointer now, because we're not putting it, we're trying to get it. And tile value commentary is decimal and binary. So we're going to nuke this commentary. So there's some commentary from the other file we need to nuke. This tile value thing, we could, I guess... Well, no, tile value is... yeah, let's just get rid of this. We could throw it down here, I guess, for reference. Like right before we send things back, we could, reference it over here. Then let's change the beginning of this thing. So we should say, references are never null, right? References are never null. And just do our little bound, right? We have the bounds check, but we don't want to bounds check tile value. We just want to make sure that it's not null, because we're using it as like a pass by reference, right? Because all a reference in C++ is a pointer that it cannot be dereferenced and it cannot be reassigned. That's all a pass by reference is. It's just syntactic sugar on top of a pointer. Okay, so tile value, and what are we gonna do here? We're just gonna say, assert that take a void pointer of 0. Make sure it's not equal to the tile value, right? If that memory address is null, we have a problem. That's all we need. I'm kind of sick of making specific error messages lately, so I've been using asserts all over the place. And that will kind of suck for if these asserts end up in production code and a customer gets it and they get a runtime assert, because then I'll have to make sure that I have the same build as them. exactly to find the line number, whereas if I have specific error messages in my, like, error functions, it's going to be easier to see what's going on. Okay, so yeah, tile value. Let's look at where tile value is used in more places. Previous tile value is this old value. And old value is actually what we want, right? Tile value, old value is this thing here. We're going to do this stuff here, and we don't need all this. This is commentary for the other function. So let's just say, let's do a new video ID of, like, right before we nuke this away. So at vid iid, we'll do, oh god damn it, I'm not showing the screen. Okay, so okay, so can we quickly explain what we did? So most of what we just did here, because I didn't show the screen, is this get function is basically a cut and paste of all of the put function stuff, right? So it looks like, you know, if I make sure that I make video commentary timestamps, it stops me from hiding this screen when I forget about it. But so over in this get function, we basically cut and pasted a whole bunch of stuff, and we had to, like, rework things a little bit. Make a references are never null check here with the tile value, and then not do a bounds check on the tile value because it's an output parameter. And, like, everything was basically the same. Old value is actually the thing we want to return. We could just keep it named old value just to keep the symmetry between the two similar blocks of code, because a lot of this is the same, so much repetitive stuff. But yeah, so right here, we're about to nuke all this code, because we're going to nuke this code, and it's really this old val thing that we need to keep, because that's the thing we want to return. So we're going to do at vid 0072, and the time is 4 hours, 8 minutes, and we'll say 50 seconds. Okay. So, and we can nuke most of the bit shifting code copied from the put function and just keep the fetch of old val. Old val is the value we want to load into the output parameter, right? Okay, so now that we know that, we're gonna nuke this. Bam! Okay, nuke that, and then we're also gonna nuke this guy right here. This stuff, no, we don't care about that. Bam. Out of there. Now, there could be some variables that we don't need to use anymore if we do this. So if we look at this, old val equals all this shifting logic and whatnot. We already confirmed this was correct, but we could look at it again. So var U08, we're getting it from the CPU pixel allocation, and we're offsetting it based on os_loc index, the local offset index, multiplied by 2. So the local offset index is going to be either 0, 0, 1, 2, or 3, and then we multiply it by 2 because we see there's 2 bits per color, or for tile value, right? It's 2-bit color for the tile value. And that's so we can make use of, just make maximum use out of the data. I won't rant too much about that, but yeah, this old val here. So this is tile value / old tile value, or old val decimal. And this over here is, you know, tile value or old val binary. And let's get rid of the little stars here like this and kind of do it like this. Okay, 1, 2, 3. Okay, and then we're going to, this return statement is no longer this blank return. It's, oh, actually, no, it is a blank return still. It's a return, right? It's still, still returning return via output param, right? Make a note that, you know, we're returning via an output parameter, so that's why this needs to be a blank return here. And to return via output parameter, we're just going to take a dereference of the tile value that went in here, and we're going to set it equal to that old val, right? So bam, old val, we got you, and we returned you. So let's just say, you know, return via output param, right? Let's make a little section for that. I don't know if I want to glue this next to there, but we might not have enough room otherwise. Oh, we have just enough room. We have just enough room, so let's do it. And let's indent that. Let's take this over here, blah, blah, blah. Okay. So that looks good. Now, there's probably some variables that we're not needing to use anymore, like this array dex. Doesn't look like we need it anymore, because we're not in the getter, or we're not in the put logic. We just don't need it. So we could kind of get rid of that for a second. So anywhere we see array index, we could just kind of comment that out. Like I'm not ready to delete it. I'm not that confident, but I'm fairly certain we don't need it. And also the compiler will probably complain. But I want to notice the similarities between these blocks of code and see how much is actually a cut and paste. And I think that keeping this here for reference will kind of help me realize, oh god, a lot of this is very similar, right? So just comment out array dex anywhere we're using it. Okay. And that should be all we need. Out of range, I guess my dude is the same message as the previous, right? Because we cut and pasted this. So I guess OOB PAINT5D OOB problem, and I don't know, man. Just out of bound problem for the this is the put function, right? We do put, then we get. So this is the get. So out of bounds problem 2021. Year 2021. Yeah, let's do that. Something like that. And let's make it kind of symmetrical, right? Let's go up where we're making that same error message, like way up here in the other code. Where the hell are you? Yeah, this right here. Let's paste that there, and this should be the put, right? So same exact message, but for the get and the put. So this should be the put, because it's put then get. Yep, put then get. Awesome. So then we can jump back down to the get error and be like, all right, here we are in this get function code, and the old value is all we need. So this old val, so that's interesting, because old val, we just want to implement. We did it because we're like, we're not going to need this, but it would be easy to implement, so let's just do it. And it turns out, hey, well, when we cut and pasted that code, this was the actual calculation we needed, so that was kind of nice. Okay, what else? I think we're done here. I think that we're ready to roll with this. I'm sure we've made some type of syntax mistake, but once we get the syntax all cleared up, we're going to be done for today. And I guess we did all that correctly, because this is not a variable in 1204, right? It's way down here. So let's see where 1204 is and see what we did wrong here. 1204, no, in expansion of macro I32. I32 is here. Oh, yeah, because, right, this thing here, we have to remove the type in front of here, so that's pretty simple. Now, what is amount to translate in pixels? So, translation, translation integer amount x, right? That's kind of like, if we want to talk about what the abbreviation kind of stands for, Alright, that's what that translation stands, that abbreviation stands for. So, right, when we clean it up, we might as well take the time to add a little bit of extra commentary to it. Okay, so delta something or other undeclared 1390. So now we're kind of like getting into this is like the move camera stuff, and I don't know how far this is going to take me in terms of how much more extra stuff this is going to make me do, because I'm kind of like sick of this right now. So okay, we're at like 4, so let's give it like at 4:30 in terms of the stream time. If we haven't finished this and come to a good stop point, we're just gonna stop because I'm sick of this. I am sick of this. 1390. So 1390, way down here. Way down here, 1390, huh? Well, that's good that we kind of skipped over a lot of stuff. So this Delta TV is not declared. And Delta TV, are we lucky enough that we actually kind of like made a notation about what Del TV is? So if we do like Del TV means Delta tile value. Okay, cool. And this Delta tile value. Oh, wait, hold on. So Delta tile value is this looks kind of like a typo because we see Delta TE here. So if we go, let's clear this out. So right, we see this TE here, we see this TV here. Doesn't that look kind of like a mistake? Like we might have cut and pasted something. So if we go up here, we can see Delta tile value, we got a TV, right? And then Delta tile exponent. Yeah, this looks like the result of a bad cut and paste job, right? So let's change that. So tile value plus this, right? Applying an offset and then capping it between these ranges with a special cap macro for a capping function specifically designed for this subsystem. So the nice thing is all of my little utility functions, because they are namespaced for this specific file, can have very specific signatures for the very specific use cases for the subsystem they're in. And like I said, I don't like utility files because you just forget what's in there, and they end up these gigantic God objects that do too much stuff. So utility functions are in the same file that they're used with, and they can be therefore more specific in terms of how they're used. Okay, so that looks good. Let's just give that another run and see what we got here. U1, U2, U3. U1 is undeclared, but what about U2 and U3? So U1, U2, and U3 mean unused 1, unused 2, unused 3. And it's in 1476, so you got to move up a little bit further. Cool. U1, U2, and U3. So these are pixel values. So these are uint32 values. So value brush, we can see U32. So we just need to declare these variables. Maybe we can make a note that this is declare variables section. So U32, U1, U32, U2, and U32, U3. And right, these are the unused variables. So unused number 1, number 1, number 2, number 3, right? That's what they are. Let's see if we can kind of indent here and create a variable declaration section. We're pretty close. Tile value on brush, whatever. We could change that trap value, make it a little bit smaller, and then we could get away with that, right? Let's just make a note here. Let's just make a long-handed note here. So, val bruh is the current tile value val, current tile val loaded into Josh's tile brush brush. This is what he is currently painting with. Okay, and then the val cur. What does this mean, right? This is a very shorthand comment, right? So why not expand it, right? We lost some column space, so why not expand the commentary, right? That's kind of what I'm doing here. Tile value on the canvas. Okay, so this is the current tile value found on the canvas that Josh is painting on. More precisely, a tile value encoded tile value encoded into a section of a byte of an RGBA pixel stored in a CPU side bitmap known as, and the name of that, let's find it really quick. It's in pixname. Did we close pixname again? Yeah, it's in pixname, so this guy right here. Okay, so we have this big long note where everything was kind of a small, so we took this kind of shorthanded stuff, and now we have a long-handed note on what that means. Okay, so we also want to take like a video timestamp of where we are in this code. So let's just do a, at vid IID, and 4 hours, 23 minutes, and 45 seconds, and, we made a mistake here, because that is not how we want to do this, and now I'm scared to think that I screwed up in other places. So, we want to do that, we want the video ID and the time. So, value brush, that is this thing down here, val cur, this thing down here, and little descriptions about what they are. So the value brush is basically the tile value loaded into the brush in the editor, the brush that Josh will be painting with. The value current is the actual tile value that is currently on the canvas, and the actual canvas data is this thing. And when I mean canvas, I mean a bitmap, or I mean a texture, but sometimes I'll loosely refer to it as a canvas. So that's good. What else are we missing here? Oh, we said that we were going to turn this into a section, right? So variable declarations. I can't spell declarations. So this is a variable declarations section because we had all these other sections and it seemed kind of asymmetrical because we didn't have this consistency with all this kind of loose code. So now all of our code has like a little section. Variable declarations, get tile value loaded into brush, get current value on tile map, brush chords read, and is that all we need to do? Okay, so toggle tile. Okay, so we're gonna get the tile value, the current value, cool. And we're gonna get the tile. Why are there two gets here? I kind of remember, but I don't remember. So brush X and brush Y. Right, because the brush X and the brush Y is literally stored in texture memory. Well, not texture memory, but it's stored in the tau. So brush chords read, yes, that makes sense. So we get these brush chords, cool. Okay, but we got the brush chords, but we didn't do anything, did we? We got the brush chords, but I don't see any toggling of the tile, do we? Get. We got a get. We got these all these gets. We got these gets. We got these gets. Nowhere here is, as far as I'm concerned, there's no toggling of the tile, right? We got all this, and we need to so here's what we're gonna do. This looks like the next spot we want to look at and do we have the current tile value? Get tile loaded into the brush. Yeah, so we have the... Yeah, tile value loaded into the brush. This Valcur, where's Valcur? Okay, so here we're looking at the current value. So we're looking at the exponent layer, the local, whatever the heck. Set or unset the tile. Right? That's what we need to do here. So let's do a little air. We're at like almost 30. Let's do air, set or unset the tile. And we might want to make a note of, like, if the value loaded into the brush is the same value as the value currently on the tile map, we will unset the tile. If the tile values do not match, then we will set/overwrite the tile. And for unset, we could say unset/erase. Okay. So another thing I'm thinking about is we need some way to kind of test out some of this stuff, right? Like, we need a way to, like, run these UI style functions and make sure they can work. So if we look at the unit test code, unit test, what I think we need is we need to take this and say there's two tests that we really need. So let's go U32 and create AAC 2020. Let's create this over again. Let's just take all this and let's subdivide this again. So we're gonna do unit test. We're gonna say unit test. How do we want to unit test? We're going to say unit test prog controls. Okay. And then let's actually make, like, the ext vod, whatever the heck's VOD, right? It's the forward declarations. These should match. And we can kind of, you know, duplicate this, say, you know, ext VOD. And then VOD. We have, that's for extern void, right? But macros. So user controls, so prog controls. Pragmatic functions that the end user does not directly interface with. User controls. Functions that are directly or near directly called as the result of user input, such as key presses. For example, let's do a for example. We gotta find one of the examples. It's like set tile, whatever, but we forgot what it was, so let's find what that is. But yeah, we have all the untested functionality, and we had notes about it where it's like, okay, we had these notes somewhere where in PAINT5D maybe? No, in our notes. So in PAINT5D notes, I believe at the bottom of the file, we're like, oh yeah, we need like these things here to be tested, right? And these are really kind of pragmatic controls. You know, for example, you know, move brush XY, toggle tile, for example. And, for examples. Well, we won't put all of them because there's more than just two, and right. But okay, so we got prog controls, we got user controls, and if we highlight these, we can see them kind of here, right? So prog controls is already this thing, right? This is prog controls. This is already what we wrote a while ago. So let's take this and say prog controls. That's what you're now, and you're now void. You're now void here. And this is void. Awesome. So all that stuff is behind us. Now because that's so ridiculous, we really want to make sure this doesn't get completely out of hand now, don't we? We're gonna make a little block that says, you know, unit test prog controls. And we're gonna have to make this kind of like a big kind of like little block here to make sure that we know this is like a divider here. And unit test, prog controls, and below, right? We're gonna have below and above. And let's do kind of one of these deals. Or one of these more obnoxious kind of deals. And let's duplicate this. But yeah, because I didn't realize we were gonna need another section. And we've already kind of sectioned the heck out of this. So let's take this unit test prog controls. Go all the way down to the bottom of all this unit test code we've already written. And down here, we're just going to say, bam, unit test prog controls above, right? And actually, we can take unit test prog controls, and we can just go prog controls, right? We can go bam, back at the top, right? Okay, below. And then let's take this, and let's paste it, and say user controls. And the reason why the user controls are further up is just because it's going to be more convenient when we start to write all this code to have user controls kind of like in this section. So below and above. So below, above, right? And then we can start writing code in this section here. And yeah, we can just start writing code in this section over here. I'm going to start off with something like, this U32 isn't used anymore. It doesn't even exist anymore, so let's take that. And let's take this functionality here, right? And this is also a main kind of thing to like call all that code. So this thing right here. And let's kind of flesh out all these functions we need, because I think we have all these functions here. So why don't we, let's look at the indentation here, right? We're not indenting anymore, are we? I don't think we are. So let's try to indent this like this, just so that, you know, now that we know we have this extra section, why don't we try to indent, right? And it's going to change the formatting of the code, but let's see if we can get away with it. So let's say that we have void, and we have this PAINT5D unit test, whatever the heck. How did we do these? Did we do like unit test code? Yeah, we kind of summarized it a bit. So void AAC 2020 PAINT5D UTC for unit test code. And then we're going to take like all these different things, right? All these different things, we're going to put them into kind of like a thing here. Hold on. So we're going to take this, and we're just going to say 1, 2, 3. We're going to replace this. Actually, we could just say star, 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 star. I don't know. It doesn't matter. So here's the thing, and then it's void, and then, you know, some code goes here, and then eventually we got to like return. And also, before we screw this up, we do not want any of these characters at the end of our functions. They don't allow it in the code, so let's not do that. Okay, so UTC, whatever the heck, and, you know, a divider would be nice. Dash line I 2x64, and a return statement would be nice. And then let's just take this and get a template for this. And actually, before we do this, let's do, you know, air, and just say, you know, to do finish test, and let's make 3 stars here. Right, so we have a little air macro for, you know, we got to finish this test code. And it's not a vital to-do or anything. It's actually we're not gonna compile until we get this finished. And now that we have, like, what I would say is a decent template to go with, you know, maybe I made some mistakes. Void this thing here, void that, no parentheses out here. Okay, that looks about good. So let's take this and run with it. So put this in the source, and we're gonna look for 3 stars, right? 3 stars, 1, 2, 3. And then we're going to replace it with the replacement keys, which are going to be all these things here. Move camera, zoom camera, all these different things. I think those are all the commands. That's all the commands we made note of. But let's before we kind of do this, let's see if that's true. So uniform controller function. So I'm going to guess that we kind of put everything kind of in the same kind of section. Yeah, uniform controllers. Well, the uniform controller functions kind of use all of the pragmatic functions. So, move camera, that's already there. Zoom camera, that's there. Move brush XY, that's there. How about the delta mutate? Delta mutate tile value, yep. How about the exponent? Same thing. How about tile layer? Tile layer's there. And the toggle tile. So, okay, it's all there. It's all accounted for. So that's cool. So let's just do, god damn it. User control. Lost my spot. Wasn't too hard to get back to. So, find keys, replace keys, source. Okay, we're ready to go. Let's take this. Let's run this. And there. So we got like a little template kind of going here. It could be better. One of the things is we could have divider lines between these different functions, because there's a lot of them, and we want to kind of be able to see very quickly where one function ends and one function begins. So let's do this. Let's throw this in here like that. Okay, so prog controls is kind of special. So I don't know if we want to change the indentation level for this one. I don't know. But what I do see here is this got to go. Okay. So now that we have these unit test code functions, we need to do something similar with a for declaration for all of these, right? Like how we did it in, yeah, we need like a for, just take this, let's just steal this. Okay, so xvod, whatever the heck. And this is one of our functions. Right, so we have for declaration, then we call the function, right? And we do that so that we don't want to adhere to really strict ordering constraints with the unit test code, just because there's so much unit test code that it really clutters things up. So we use a for declaration to say, hey, this stuff is, well, usually for declaration means that it's definitely below. So we should probably stick to that as well. The idea here with the unit test code is we want the general summary at the top, because, man, there's so much unit test code, we really don't want to have to dive into it all and be, like, overloaded by front-loading all of it, like going from... In the C code, we usually go from the most general, simplest functions to the most high level. That's usually the order we go, just because we don't use any for declarations. However, in the unit test code, we really don't want that. We really just want to be able to write the unit test code and forget about it. But if we ever want to come back to the unit test code, we don't want to be overwhelmed, so we want to see like the main function and see the high-level overviews. So we want to take a like clean code approach to that kind of organization for this unit test code. Okay, so we got this, and that's all we need for the for declaration. We want to align this nicely. And if we're going to do that over here, we might as well do it over here. Let's get a template for this, so farc template. And we still have the references over here, right? So we can take these, we can copy them again. And we can paste right there, and, oh, maybe not like that. Let's make a little bit more room. Paste right here, cool. And we're going to look for, once again, 3 stars, 1, 2, 3. And the source code is this thing right here, right? So let's just take this whole thing, copy it, and paste it here. And then go Control-C, farc, and run that. The alignment is horrible. Okay, that's better. Still looks a little bit horrible. But let's move this over here like this and be like, okay, what's violating our alignment here? And this is, okay, so these are all over. So if we want some type of consistent formatting here, then we're going to have to put the extern voids at the top like this, right? Just to, if we want to not go over a column limit, but we want to keep all that spacing uniform, then we're going to have to do this, right? This is just the way it's going to have to be. All right, because then what we can do is we can just indent everything to the same level. Right, smash that, move it over, and now you have just enough room for this function, so that's good. Okay, so just a big little list of all the stuff that we need. This is just a thing to get us started. Okay, cool. So we have all the functions that we want to call, and right now they're all just these are all 1, 2, 3, 4, 5, 6, and 7. So we got 7 of these. 1, 2, 3, 1, 2, 3, and I lost my place. It seemed like more, didn't it? 1, 2, 3, 4, 5, 6, and 7. Okay. 1, 2, 3, 4, 5, 6, and 7. Okay, you know, it's 7. I just can't keep track of this. So all these have, like, different to-do messages. To-do finish test, right? And then they're named after the test that needs to be finished. So we have all these tests kind of stubbed in there, ready to go, right? Because we're kind of sick of this, but we're like, we need to clean up these kind of loose ends before it's too late, before we lose track of it. So any opportunity to add more code in a place to help us clean up our loose ends, we're going to do it. Because we've been all over the place. Also, this is wrong. This comment character needs to be this. Okay. Well, I don't know what other stupid mistakes I've made, but let's give this a run, see what the next mistake is, and then we'll probably just give up pretty soon here. They are a tile exponent undeclared, first use here. Okay, so 15 something or other, the heck. 15, 17? Tile exponent, what do you mean oh, yeah. Toggle tile, interesting. Oh, yeah, because, right, it's getting all of its information from the different textures and things that were set up. So it makes sense that it would be like that. Now, tile exponent is nowhere to be seen. The tile layer, tile layer. Okay, which things are not actually here? Hold on, so which things are not actually here? So, what things don't we have? So, like everything. We're missing everything. We're missing all this stuff. So we need to actually get these things, right? We have the brush value, but we do not have... So we got get tile value loaded onto the tile map. Variable declarations here. So we need another section where we're getting the, like up here, get current tile value on the tile map. Get brush settings to locate so we already have the val cur. Wait, hold on. So where's this tile value? This val in the brush, right? So you got the value loaded into the brush. So really what we need is we need a section here. So we're going to take this here. And we're going to make this another section. Because what we really need is we need the value loaded into the brush, but then we need some other stuff. So this is tile value. We'll call it tile value here. Right, so this is the value loaded into the brush. Val brush, right? Tile val. And we're going to call this section get tile brush variables. Right. Get brush state, right? That's kind of what we want to get here. We're kind of getting a state. Okay, get brush state. Cool, that's cool. Okay. And get the tile value loaded into the brush. And let's make a little section here at the very top. Let's make a little multi-line comment here of what we need. So, variables we need from this section. 1. We need the val brush. We need this value of the brush, right? We also need tile exponent. We need all these guys, right? So let's see where everything is declared. Value brush, but we don't have tile exponent, etc., right? Yeah, we're missing that. So we need to declare those. Value brush, and 2, tile exponent. 3, the tile layer. 4, the local TX location of where the brush is, and the local TY. Now, as far as this local, this val cur, that's actually the thing we're going to fetch. So we don't need to get that. So we're gonna do this, like, I don't know if this is the best formatting. Right, we obviously have a lot of extra space here, but the idea is get brush state. We have this nice little commentary kind of like glued up against here to kind of enforce the nesting. I don't know. But yeah, so we got the value loaded into the brush, and then we need to get, let's just say, I'm just going to call it get state. And we're going to be kind of regular. We're going to be more regular about this. We could just make a note of this. Right, that's what this is, but let's be more uniform. So let's call this get state. And this is val brush, right? The value loaded into the brush. Cool, we got this get state tile exponent. And a lot of this is going to be kind of cut paste, right? So we should probably cut paste if it's going to be cut paste. So tile exponent right here, and then we need to paste this 1, 2, 3 more times. So let's do, you know, hashtag error and get state tile exp. And then we'll paste this 4 more times, we thought. Yeah, because we're in tile exponent, and 4 more times. Yeah, 4 more times. 1, 2, 3, 4, right? So all this get state stuff. So let's call this get state of brush. Right, so that way when we highlight get state, we can see it in all the other states, all the other sections. So get state of brush. That's what we're going to name it. So that way we can just see, hey, there it's all lit up, right? Oh, hold on. So it's all lit up. That's cool. Get state of brush. Cool. Now, what do we got to do here? So we kind of cut and pasted here. So there's tile exponent, but then everything else, this should be like, we should just use our auto complete kind of script here. So let's farc template. It's going to just be quicker if we use this template. So take this state for the tile exponent, and we're going to look for tile exponent like this, and we're going to replace it with these 4 other things, right? Hold on. Why did we paste it? I thought we said paste it 4 times, but this is all we need. 1, 2, 3, 4. We need 4 things total down here, right? 1, 2, 3, 4. Here, you know what we're going to do? We're just going to take all of that. In the replace keys, we'll just do this, right? So we're going to override itself like that. Take that. Bam. There we go. And this... 2 of these are identical, right? 2 of those will be identical. That's fine. We'll just delete those. And there we go. So now we have get state for tile exponent, tile layer, location. So we got to figure out how to do all that. But now it's kind of stubbed in there. It's kind of ready to go. And we'll figure that out later. So let's run this one more time, kind of see what happens. And as long as it's like error, okay, there, it stopped at where we put the error message. So I'm happy with that, getting the tile exponent. Okay, that looks good to me. But yeah, I'm sick of this. So let's do get bash here. And do get status. Get add dot. Get status. Get commit dash am. Finish your fucking... maybe we shouldn't do that. Finish your functions. Okay, so... we've reached another hour. We've kind of stubbed some stuff and we've cleared up some loose ends. So now it's time to just kind of do some more push-ups and then call it a day, because I'm sick of this. Okay, so yeah, let's do more push-ups, and also let's look at how many push-ups we need to do, right? So, we only said that, you know, we're gonna do 10 per hour, but if we do 20 instead of 10, we'll be at 100, right? So, let's check that out for a second. So, push-ups, 4, 4, 8, right? That's gonna be 5, that's gonna be 90. But yeah, if we did 20 of each, we'd be at 100. And so let's just do that to get those 100 in. And then, yeah, and then we'll be done. We'll have done our exercise. And then, you know, after we do this for a little while, after we've been doing this push-up thing for maybe a month, we can see if we need to do more exercise or less. Right, we'll take a look at our weight, see if our weight is going up, down, compared to where it has been. And depending on where it's gone, we're going to be like, we'll have to up the pressure, right? So the idea is we don't want to make huge changes to our lifestyle, because if you slowly are getting fat, then you want to actually slowly get rid of the fat, right? You don't want to do anything drastic. So if you're slightly off homeostasis, right, you're just slightly in, you're just consuming just a little bit too many calories, then the idea is just to add a little bit more exercise until you can figure out what needs to be done. So let's do our 80 push-ups and then get out of here. Be done for today, at least. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, crunches. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Squats. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so let's update this list. This is 100. We've basically been streaming for about 5 hours. Let's look at our agenda screen. Tile camera, keyboard inputs, PAINT5D get put, unit test get input, and then actual texture call to OpenGL, the texture push call. Okay, let's look at what else we got. Agenda to be continued at a later date. Next time, PAINT5D camera. So, I'll see you around. You know, I'm talking to myself, but that's kind of cool because when I make this awesome stuff, I'll be the first, and I will have been able to like publicly broadcast. And yeah, so I think this is cool. Later.